Looking to see if our speakers for the morning are here yet. I don't see Cheryl. Cheryl, are here under an alias? And how about Patrick Orenstein? Oh, there's Patrick, I see him. I see Zhang Lin. All right, Dan, should we get going?
I think so. All right, thanks everyone for coming. It's a pleasure to be here. Remember the UCAR code of conduct here, as always, for UCAR meetings. I'll go to the agenda. So after this brief introduction, Frank is going to give a little status update. And then we'll have 3 talks. Recording in progress, got it. And then we'll have 3 talks before the break. At 10 o'clock local time here, we'll have a 20-minute break. And then we'll kick off a session on waves in MOM 6. And that's a series of shorter talks, which will end at about 11:25. So my slide here is not quite right. I think we have one more talk at 11:20 that's short. At 11:25, we'll then have 25 minutes of open discussion on waves. Or no, at 11:25, we'll have discussion on waves. And then after that, a brief open discussion on whatever we want to talk about. And we should be done by noon. Just a couple of reminders. So we are streaming this live on YouTube, and then it will be recorded and available for anyone to watch on YouTube. Also, just a reminder that the text, whatever you put in the chat, is saved, can be saved, including private messages, not just ones that are to everyone, but ones between each other. Those are saved as well. And I think that is rules of the road. So keep your microphone muted during the presentations, please. If you have a question during the talk, please just use the chat. And then we'll have Q&A after each talk. Oops, sorry about that. And during that time, there's a lot of people here, so please use the raise hand function in Zoom, and Frank and or I will monitor the raised hands and try to moderate that. So that's it. Thanks.
Yeah, just let me, couple of addendums on the agenda. So the only change in the agenda is Alper Altuntas will give a very brief kind of a status update of where we are right now with respect to coupling WaveWatch 3 and MOM 6 as the last of those short talks on wind wave issues, and leading into the discussion to sort of set the stage of where we are, so we can be talking about where we want to go. And then the other thing is that we do have this Zoom call for another 30 minutes after 12 o'clock. So we don't absolutely have to finish at 12 o'clock. Okay. In terms of status and updates, I didn't actually prepare another presentation, but this I can show what I showed on the Monday plenary update if people want to see something. But let me just put it out there. The the process on Monday was we blasted through all whatever 13 or 14 working groups without an opportunity for people to ask questions. So this is your opportunity to ask questions about the Ocean Working Group update, or if you want to see something again, now is your time. Just go ahead and raise your hand or unmute and ask a question.
Frank, I have a question. This is Nikki.
Hi, Nikki.
Hi. There's a lot of talk about Wave Watch 3 and representing waves in MOM 6, and I'm wondering if there are plans to eventually transition that to the Marble interface, in the sense of representing bubbles and their role in gas exchange or things like that. Could you speak to that a little bit?
I think that's an excellent question for the discussion afterwards. I hope that some people might want to talk about the role of waves, breaking waves in air sea flux calculations. And I'm not the person to really, I'm not really informed on that issue. So maybe we can come back to that at 11:25.
Okay, thanks.
Yeah, I think it's a great question and direction, and something to be thinking about. Other questions about the presentation on Monday? Okay, let me just give you a little bit of a sort of expanded description of our status. So in terms of our configurations that we have available, I showed on Monday these different vertical grids we've explored, and much of that material was actually shown at our winter working group meeting. Since that time, a couple of things have happened. One is that Gustavo and Keith Lindsay, working with folks at GFDL, have kind of reworked the implementation of passive tracers. So we have CFCs going sort of as our first test. So we'll be able to use those in the evaluation of vertical grid and any other parameterizations that we're bringing into the model over the next months and years. The other is we have made, if you caught Peter Laritzen's talk in the AMWG yesterday, and this issue that I brought up in my presentation with respect to energetics of the system. And just to expand on that a little bit, if you recall, POP is a constant volume model. So we don't actually exchange fluid mass between the ocean and the other components of the hydrologic cycle. So when it rains over the ocean, we don't actually add water, we remove salt. It uses a virtual salt flux boundary condition. So we remove the amount of salt that is required to achieve the same dilution of the surface layer with respect to salinity. So that made things much simpler, well, somewhat simpler in terms of the energetics, because that water moving from the atmosphere or the rivers into the ocean carries some enthalpy. And we didn't have to account for that because we weren't adding any mass to the ocean. We didn't care about what the enthalpy of that mass we weren't adding is. And as it turned out, the atmosphere didn't care about it either. But now that we have a model with a natural boundary condition, we have to account for that mass. And we went through a process of sort of evaluating how big of a term that is, and it's non-negligible. Locally, it's tens up to 100 watts per meter squared. And in global average, it can be approaching a watt per meter squared at times. So we really do have to close the energetic budget of the system. We have this term in MOM 6, but we don't have the matching terms in the other component models. So again, Mariana and Gustavo have implemented a first cut at this and being able to exchange those energy fluxes associated with mass exchange. But as of today, the other component models are not accounting for that. So we're working on a strategy with the other working groups on how to deal with that. And it's not as straightforward as, you know, the complexities of the atmospheric thermodynamics are quite a bit bigger. It's more complex than our system. And additionally, our river transport model has no thermodynamics. There is no way to exchange energy with it. So we will need to design and implement some kind of a global fixer to account for that energy deficit. So those are some of the things we've been working on as within the ocean section with our resources for in terms of liaison effort over the last couple months. Steve.
That's good to know that you're doing that, Frank. I know at GFDL, we've been from the ocean side trying to get the atmospheric people to do this for more than a decade, and they say it's a really difficult problem with parameterizations and just lots of details that are difficult to deal with.
Yeah.
Are you thinking that you're going to have your act together for all component models to have a closed energy budget for the next coupled model with MOM6? Or is there going to be a stage in which you're just going to call it a day and move on and just kind of like what we do?
Well, I guess our initial target is to close the terms that are straightforward to close, and then put in a global, some kind of a fixer for the terms that aren't. So for example, river runoff, there's just no way to do that from first principles in our system.
That's interesting, because for us, the land people were able to deal with that much easier than the atmospheric people. I wonder what the deal is with the river.
Our river transport model has no doesn't carry a temperature. So
Okay.
there's no thermodynamics there.
Yeah.
So yes, and you know, as Peter described yesterday, it is a very complex problem in the atmosphere to keep track of enthalpy in all the different states of water substance in the atmosphere and how they're moving around. So, but we do need to close the budget globally, at least in an ad hoc way, so we don't have spurious drift in the system.
Yeah, I would just be careful with doing global adjustments, you know, like we do with core and JRA. You know, for the salinity or for the fresh water, it can be big in places that are just non-local.
Yeah.
Yeah.
Okay. But we've sort of been holding off on continuing our evaluation of the configurations of MOM6 we have until we can run stable coupled runs. And we're sort of stuck at this point to come up with something that is at least energetically consistent.
I guess one sort of very unsatisfying perspective from the ocean side is to put a virtual option into MOM6.
Yeah, that's really unsatisfying.
Yeah.
So. All right, Bill, Large?
Yeah, I just wanted to add, if you listen to Peter's talk, in what he's doing in the atmosphere, he's making approximations and say if we're below, I think it's something like 0.01 watts per square meter, then he is neglecting it. So whatever we do, we should sort of have a consistent, a negligible kind of number because that's what he's doing. So we're not going to be down to the 10 to the minus 6 or a round off. It's going to be something like that. I forget what it is. It's
yeah.
So there is some limit to what he's trying to take the atmosphere and get those equations going. So right. We should be comparable, I think.
Yeah, the other thing I heard was, well, I didn't hear it. It was actually a thread in the chat during Peter's talk, was that apparently the NOR ESM group, which runs CAM 6, has addressed this issue in their version of CAM. So I think it would be worth following up with them to see what they've done. All right, it's 9 o'clock. Ian, you want to take back over here?
Sure, I've lost my agenda.
Okay, first up is Zhang Lin Wen. Her title is The Impact of Atlantic Meridional Overturning Circulation on Marine Heat Waves During Climate Warming. So Zhang Lin, you want to go ahead and share your screen? there.
Okay, can you hear me?
Yes,
And the screen is
looks good.
normally.
That's good.
Hello everyone, I'm Charlene Wang, a first-year graduate student from the Department of Earth and Planetary Science of UCR. And this time I would like to share with you my recent research progress on marine heat wave and in collaboration with Dr. Liu. And the topic is the impact of Atlantic meridional overturning circulation on marine waves during climate warming. And since the 1980s, land-based heat waves has been occurring frequently in response to the continued global warming. More frequent and intense marine heat wave events have accompanied the rise in the sea surface temperature. Marine heat waves are annual extreme warm water events that can last for several months and cover an area of thousands of square kilometers. As an extreme climate event, marine heat wave can have an impact on natural environment as well as on human society. And in recent years, many scientists have conducted research on marine heat waves. And because marine heat waves are anomalously warm water event, increased sea surface temperatures greatly increase in the likelihood of marine heat waves. The figure on the right shows the result based on the OSST version 2 observations. The global mean surface temperature continues to increase during the global warming process. Correspondingly, the frequency, duration, and intensity of marine heat waves shown an increasing trend. And generally speaking, global warming has led to a higher frequency, wide attack range, and greater intensity of marine waves. And next, some introduction to about the AMOC. The AMOC is a major mechanism for heat redistribution on our planet and an important factor in climate variability. And AMOC is a sensitive system on the subtle temperature, salt, and density differences in the ocean. And the right panel shows the shows the change in AMOC over time in the climate model, where the dark blue curve indicates multiple model mean. And we can see that after a long and relatively stable period beginning in 1860, AMOC experienced a rapid decline in the mid-20th century. And the weakening of AMOC is also confirmed by the further observations. The left panel, A shows the degree north from the measurements and showing that the circulation has weakened in the last decade. And the left panel B shows the change of AMOC index. The AMOC index defined as the difference in surface air temperatures between the subpolar North Atlantic and the Northern Hemisphere. This index indicates a negative trend in the AMOC intensity over the past century. And therefore, as predicted by climate models, the AMOC is slowing down due to anthropogenic global warming. And the study has shown a gradual increase in marine heat wave events occurring during the process of global warming. And meanwhile, AMOC has been gradually weakening in recent decades. And this next leads to the scientific questions that we will explore. Will the slowed AMOC have an impact on the marine heat waves that has been increasing? And if there is an impact, how do the marine heat waves change under the weakened AMOC? And how does AMOC affect the marine heat waves? And these are the focus of our research. And then we used the sea surface temperature observation from the daily OSST version 2, which covers 38 years from 1982 to 2019. And this data is of good quality and high resolution, and has been widely used in recent years for marine heat wave studies. Because our aim is to explore whether the AMOC will affect marine heat waves and global warming, we need to control for the changes in the AMOC. And we used 5 ensemble members from the system for historical and RCP 8.5 simulations, and focusing on daily sea surface temperature information. The study time period as 1981 to 2020 and 2061 to 2100. To explore the effects of AMOC on marine heat wave, the result of a set of experiments, AMOC fix, were chosen as a control. In this experiment, fresh water removed from the vast deep water formation zone in the subpolar North Atlantic, the blue area, as AMOC remains almost stable to 1980, while global warming continues. The data used in this are shown on the right, and with right part representing the data for fixed AMOC and the blue part for normal conditions. Solid curve indicates multiple model mean, and it is clear that AMOC is weakened under natural conditions. Next, look at the calculation of marine waves. First, define the marine heat waves. Marine heat wave is defined as a discrete, long-term, anomalously warm water event that occurs at a specific location. To explore some of the characteristics of marine heat wave, scientists quantify its general definition. And first, it is based on whether the sea surface temperature exceeds a set threshold to determine whether it is an abnormally warm event. And to determine the threshold, the climatology average is first calculated. Then the percentile threshold is determined. In earlier study, high surface temperature threshold were generally set as fixed thresholds, like the panel A. And this approach ignores the interannual fluctuation and regional variations in sea surface temperature. In subsequent studies, affirming marine heat wave threshold are imaged, like the panel B, which use daily temperature values for all years within an 11-day window centered on a particular day, and calculates a 19 percentile threshold for each day, and then performs a 31 days smoothing. And this method ensures a sufficient sample size, and the threshold will vary seasonally. After we identify marine heat wave based on the daily sea surface temperature time series, and we can characterize their frequency, intensity, and duration. And duration is defined as the time between the start and end dates of the event. The frequency is defined as the number of events per year, and its intensity refers to the maximum intensity of each marine heat wave event. The maximum temperature anomaly relative event. To review the changing characteristics, we first detected the marine wave events in observations and simulations over the past 40 years. And the left and the right panel is a result of the climate model. Over in the observations and in the ocean model are similar. And in general, the model can be used to simulate the characteristics of marine heat waves in the real ocean. And in order to investigate the global distribution of marine heat waves and its development under different intensity AMOC effects, 2 time periods are selected for analysis. And the first one is 1981 to 2020. As shown in the figure, the first column is the result of natural case, the AMOC-free, and the second column is the result of the AMOC-fixed experiment. The last column is differences between the 2 previous ones, AMOC-fixed minus the AMOC-free. During the last 40 years, marine heat waves with a wide range of influence and long duration have mainly occurred in the eastern tropical Pacific, matching the region affected by the ENSO events. And the average duration of marine heat wave is about 70 days. And overall, the number of marine heat waves in the different regions is about 1 to 4 times per year. And high intensity wave then appear mainly in the western boundary, current extension, and central Atlantic, with an average annual frequency of about 2 to 3 times and a duration about twice as long as under AMOC weakening conditions are observed. The effect of AMOC changes on marine heat wave intensity is not significant in this time period, and only weak enhancements are observed in a few coastal regions. And the above result indicates that changes in AMOC rarely have an effect on marine heat waves. To further investigate this effect accurately, we selected 1 to 2100 for the experiment. Controlling for AMOC intensity, a single and persistent strong marine heat wave occurs not only in the equatorial Pacific region, but also in the Northwest Pacific, south of the Greenland, this area. And stability on the duration and frequency of marine heat wave is opposite in the northern and southern hemisphere. In most of the northern hemisphere, stronger AMOC is accompanied by longer marine heat wave duration and increased frequency, while shorter duration marine heat wave and lower annual mean frequency of marine heat wave will occur in the southern hemisphere. The exception is the North Atlantic region, the south of Greenland, where the duration of marine heat wave is so long that it is judged to be a single high-intensity marine heat wave during the statistical process and resulting in a decrease in the annual mean frequency of a result of the first 40 years of 1981 to 2020. Between AMOC fixed and AMOC free, the variation of AMOC is much stronger, and the variation of marine heat wave duration, intensity, and annual mean frequency is also much stronger. And in order to explore the variation of marine heat waves with time more visually, we selected the North Atlantic, which is most affected by the AMOC as a study object. The variation of different features of marine heat waves in the North Atlantic over time for time period is displayed. For the first attempt, 1981 and 20, the results of the two data sets are close, and the results of AMOC fixed are slightly higher than the AMOC free in the last decades. And during 2061 to 2100, marine heat waves under AMOC fixed conditions are much stronger than those under AMOC free, with overall increasing trend in duration. However, during the last decades, the frequency of AMOC fixed decreases and is lower than the AMOC free in this part. This may be related to the appearance of a single high intensity marine heat wave on the south side of Greenland. The extremely long duration of marine heat wave at this location leads to a lower calculation of the frequency, and this slightly decrease is observed after the over average, the global average. Compare the left and right column plots. It is found that the gap between the two red and blue curves on the right side is larger. This may be due to the fact that the AMOC has been continually weakening since 1980. And the right-hand side, corresponds to a smaller flow of AMOC than the left hand. So why does the strength of AMOC affect marine heat wave? And we guess that it may be related to the effect of AMOC on the sea surface temperatures. And in order to investigate the relationship between marine heat wave frequency, intensity, duration, and the sea surface temperature variation, we selected 3 regions to compare the probability density of the sea surface temperature anomaly in the different AMOC intensity states during the 1981 to 2020 and 2061 to 2100, respectively. The different forms of temperature probability distribution implies different probability of extreme weather events. If the whole distribution changes toward warmer climate, and there will be more warm events and less cold events. And if the temperature variability increases without mean change, there will be more warm and cold events. And in addition, if the distribution pattern changes, there will be astromatic changes of warm and cold events. The three regions we selected are the in this area, the Mediterranean and the Northwest Atlantic, where marine heat waves have occurred before, and the region south of Greenland, which is the North Atlantic warming hole in this area. Overall, the sea surface temperature anomaly probability density function of AMOC fix in all three regions have basically paneled out in the warm direction compared to the AMOC free. And the distribution pattern has changed with a significant increase in extremely warm events. The degree of advection is much larger in the later 40 years. 81 and 2020, the mean surface temperature anomaly values in the three regions increased by 0.05 to 0.1 degrees Celsius. And in the period 2061 to 2100, the mean surface temperature anomaly increases by 0.5 to 3.8 degrees Celsius. It's larger than the first time period. And in addition, it can be seen from the panel C that the left and right side of the AMOC fix curve are not symmetrical in the region south of Greenland, with more in the right hand, and which indicates a higher increase in the warm events. And in general, the increase in mean surface temperature is one of the main reasons for increase in marine heat waves. And the higher latitude region have a higher mean surface temperature increase and higher sea surface temperature variabilities, and thus are more likely to have higher intensity and high frequency marine heat waves.
Zhang Lin, I think we lost your audio. Whoops. We lose her altogether.
I don't see her in the participant list anymore.
Yeah, it was pretty unstable. No. Well, that's unfortunate. We are at the end of the time. I see that Wei Lu, her advisor, is on. Maybe you would be willing to entertain a question or two based on the material we did get through.
Sure. Thanks. Yes. Okay. I think Charlene has been gone through all the most materials and basically only like the final slide for the conclusion. So
Okay.
yeah, thank you very much. I'd like to take the question. I saw the chat box. How does the from Cheryl? So how does the AMOC fix? So basically, we fix AMOC by extracting fresh water from the subpolar North Atlantic, covering the deep water formation area. So by doing that, we kind of like to control the deep water formation. Basically, we can maintain the AMOC strength under global warming scenario, RCP 8.5 for this one. So that's basically what we did. So we published a paper in 2020, last year. So basically more details can be found that.
Okay. And Baylor had his hand up.
Another question from Nikki is the fixed Morgan sample output available? So we have just try to pull the data, and so yeah, if you are interested, please contact me. So high resolution, that'd be great if we can see the high resolution, definitely, and and also we realize the high resolution model compared with the low resolution, and it could be greatly affected by the resolution, especially in the coastal area. So that'd be very important. Thanks.
Okay.
So Baylor put his hand down and said thanks in the chat. So I think for the sake of time, maybe we should move to the next one. What do you think, Frank?
Yeah, I think we should move on.
All right, so next on the schedule here is Patrick Ornstein. You hear Patrick? There you are. Do you want to go ahead and share? And Patrick is going to talk to us about evaluating coupled climate model parameterizations via skill at reproducing the monsoon intraseasonal oscillation. Thanks. Go ahead.
Yeah. Hi. I think my sound's on. Baylor taught me that you can change the title of the talk if no one notices. So there's that. Hi again, I'm Patrick Ornstein, and I'll be presenting on evaluating turbulence parameterizations by their impact on the modeled monsoon intraseasonal oscillation. Just wanted to say, I'm currently a grad student at Columbia, but I did most of the work on this project at Brown with Baylor, Leah Johnson, Jing Li, who I see is here, hi Jing, and Akash Sain. These results are also included in a paper we've written, which is currently in review. Just to outline, I'm going to describe the model parameterizations we investigated, briefly describe the monsoon intraseasonal oscillation, just to give quick context, and present some of the results of our model runs, and then discuss some of the implications. Just to briefly summarize, we looked at two different ocean turbulence parameterizations in 30-year runs of CESM 1.2. First is the Langmuir circulation, which is the vertical rotating cells caused by surface wind shear, and they tend to deepen the mixed layer. And the other are the mixed layer eddies, or I'll just call them MLEs, which are caused by horizontal buoyancy gradients. Excuse me. And they tend to shoal the mixed layer. The figure on the bottom is from Fox Kemper and collaborators 2008. And it shows a temperature front in an idealized simulation of the upper ocean. The black arrows are indicating where the mixed layer eddies seen at the surface are causing the front to overturn and re-stratify, basically. Again, just to provide some context, we were looking at ocean turbulence from the perspective of the monsoon intraseasonal oscillation, or I'll refer to it as the meso. The meso is a mode of variability of rainfall in South Asia, which acts on a shorter timescale than the Indian monsoon itself. It's best illustrated if you look at the figure on the right, which is from a 2016 oceanography paper, and shows three representative monsoon seasons. The top two are drought years, and the rainfall totals are on the right, and the third down is a flood year. And so you can see that the short-term variability, which is associated with the meso, is important to both the short-term and seasonal term rainfall amounts, which upshot is makes it understanding and predicting it a topic of significant societal interest. So I'll just start by saying that to identify the signature of the meso in rainfall data, we used a method based on the work of Suos and collaborators in 2013. This involves using an extended empirical orthogonal function to decompose zonal average rainfall data. And we use that to define a meso index based on the first mode of variability. So the results of this analysis are visualized in two different ways. So the first are these maps of the difference between the positive phase and the negative phase peaks of that index in rainfall in space. On the right are shown the 4 model variations that you get by turning on and off the 2 parameterizations. So control on the top left refers to version with both parameterizations turned on. And then you can see no Langmuir, no submesoscale, and the bottom left is no Langmuir or submesoscale. And then we're comparing that on the left is rainfall data from a reanalysis data set. This sort of bimodal north-south distribution of rainfall is what we're looking for, but it's also, favored by the empirical orthogonal function method itself. But all the models consistently get us the wider east-west distribution of rainfall that's consistent with the reanalysis data. However, what's interesting is only the control data set gives us the rainfall intensity also on the west side of India, in addition to getting the north-south bimodal distribution in the Bay of Bengal. The other way of visualizing this data is to think about the length of those phases. These are histograms of the phase lengths in days from all 5 data sets. Positive is the left column, negative is the right column. You can see that the CESM runs are a 30-year run, whereas the reanalysis data set is only about 15 years, which is why the sample sizes are different. But if we look at if you look at the distribution of phase lengths, the control run, which is the second line down, gets a distribution between 10 to 60 days, and a pretty tight distribution, which is most similar to the phase lengths you see in the reanalysis. And you can see that as you turn off turbulence parameterizations, you start to get a wider distribution and you start to get unrealistically long meso phases, to the point of going to the time scale of the monsoon itself in some cases. We also looked at, tried to look from a mechanistic point of view at what might be causing these differences. Since the ocean atmosphere behaviors depend on the top layer of the ocean, it stands to reason that a model version which best recreates the meso should also be the model version which best models the mixed layer depth. However, this plot is comparing the average monthly mixed layer depth in the Bay of Bengal and between the CESM runs and a different reanalysis data set, which is the monthly isopycnal mixed layer climatology, or MIMOC, which shows that although all the model versions differ from the observations, especially in the winter, the model version with both Langmuir circulation and mesoscale eddies, so the control run, is not actually the one that gets closest in the summer. That's the blue line. So basically, this indicates that the meso result, the fact that the control run gets meso phases most similar to rainfall reanalysis phases, can't be necessarily taken as a holistic indication of the model coupling quality in the region. And it also means that probably other factors, other differences in the two model versions behavior is responsible for the meso phase result. So basically, these results indicate that the turbulence parameterizations improve the coupled model's representation of the meso. Additionally, we think that this confirms that extended empirical orthogonal functions are a robust but also computationally cheap way of evaluating model performance if you choose a phenomenon to compare them to. On that note, thank you, and I would also be happy to take any questions.
All right, thank you. Any questions? There we go. Bill Large has a question.
Yeah, this is an incredibly complicated thing you're trying to sort out. So I'm curious, have you thought, I mean, you're relying on these, the coupled atmospheric model to create rainfall. Have you thought of perhaps a more direct OLR kind of comparison to try and get rid of some of the uncertainties in the atmospheric model for producing what you want to look at?
You're saying look
Precip
at,
is really hard.
yeah, you're
and-
saying look at like cloud cover instead
Well,
of,
I'm just thinking if you've thought of anything else that might be
Yeah.
a proxy for what you're looking at, that's a little less subject to vagaries of the atmospheric model to produce.
yeah, no, we did think of that. The couple factors are one, we were most interested in rainfall itself.
True.
As opposed to looking for another proxy for model behavior. But you're right in that the reanalysis data set, just as a you know, as an example, it's in that, yes, we did think about it.
Okay.
We didn't do it, but yes. Yeah.
Frank's got his hand up.
Yeah, I was wondering about, so well, the question is about locality of the influence and to what extent, you know, is through this particular methodology, can you identify an area of the northern Indian Ocean that is where the sensitivity lies, or is it really the whole basin scale behavior of mixed layer depth and SST? I mean, obviously you're looking at teleconnections onto the continent, but can you identify with more locality where the ocean simulation is deficient in its representation of air sea fluxes?
Well, it's interesting. The meso dynamic is that it's a moving, it's not a phenomenon that happens in one place. You know, the whole phenomenon itself is a northward movement. So,
but is there like a preferred latitude band for the initiation, and is that an area where we might look in a more focused process level way?
You mean like looking at where it's breaking down?
Well, I was thinking where it was initiated, where these bands come from.
Yeah, I mean, that's where you start. I should show. I don't know which figure is best to show it, but sort of where you get these the quote unquote sort of negative dipole kind of down in the Indian Ocean. That's sort of the southernmost extent of the bands starting and moving up. That's how you get that. But to me, that was one of the weaknesses. Yeah, because since you're looking at the accuracy, you're looking at comparing the motions, sort of. You're comparing something in motion as opposed to comparing behavior at points.
Okay.
So, yes.
We do have some more time if there's any more questions.
Yeah, that went faster than I thought.
Just finished a little early. So we've got Frank. Baylor has an answer in the chat for Frank there. I won't read it out. Peter Sullivan has a question. Go ahead, Peter.
I want to see it.
Hi, Patrick. Just a simple, naive thing. Do you have any clues as to what's missing? What would move all those curves from CESM to what you think the observations are?
I think, well, one clue is how it gets so much worse in the winter. So the difference, the monsoon, we're looking at summer months here, but I think if I were to just guess, sort of the clue you're seeing is that since the mixed layer depth difference gets so much worse in the winter, it's almost like we're in this case, it sort of looks like we're overcompensating for winter mixing. But I can't quantify that right now.
Yeah, all the turbulence wants to make it deeper.
Yeah.
It horizontal transport of something might make it shoal. But no, I was just curious if you had any thoughts about that.
Yeah.
Deepak, do you want to go ahead?
Yeah, thanks. Thanks, Patrick. This was an interesting talk. I was thinking about this figure and the mixed layer depth being 60 meters, which is kind of crazy as you see from comparing to BIMOC, but it's pretty reasonable, I think, for the isothermal layer depth. So I'm wondering if the model salinity is so biased that that's what you're seeing in this figure. Do you have any comment on that?
Right, because it's I remember we were looking at we were talking about whether it's a definition problem, like you're saying, between the definition that the reanalysis set uses and the model uses.
Yeah, or maybe
not,
you're having trouble with the salinity field and affecting freshwater plumes around.
So like what there's a bias, but which bias are we noticing, basically? Yeah. So we worked on that and couldn't. We looked at multiple sort of reanalysis data sets to compare it to see which you were seeing. But yeah, I agree that that was something we were thinking about.
All right, thank you.
All right, well, thanks everyone for your questions and Patrick for your talk. I think we're going to move on next to Cheryl Harrison. I'm pretty sure I saw Cheryl. There she is. Do you want to go ahead and share your screen? And Cheryl's going to talk to us about disentangling the impacts of NPP and SST on global fisheries decline. So you're.
Hi. I just updated my I just updated my operating system, and Zoom is telling me I don't have registration rights to share my screen right now, which is a problem. Let me see if I can.
If you
guys have the PDF that I emailed to Elizabeth, or can I send it to someone to share? I can shoot it to you, Ian, if that's an option.
We have it in the folder here. Let me find it. If you want to email it
Yeah.
in the meantime, that could be great.
Email it. Sorry, email it to who?
You can email it to Ian. That would be fine.
Todd, do I have access to that drive folder?
You should. I'm looking for the link now. I'm asking our support team to get that link.
Okay, I thought I had it fixed, but it didn't. So let me email it to Ian, and I have to find it. Okay.
I'm looking for the drive folder as well. So if I find it.
I just emailed you a copy of it, and it's a link to it on a Google Drive. Sorry, everyone.
Okay, I think I just got it.
So while Ian's getting that up, I'm going to be talking about something completely different than the previous two talks, which is a report on the fisheries model intercomparison project, SHMIP, and we have a number of papers coming out, one of which is using CESM data to force the model exclusively. So I thought it would be a good opportunity to tell you guys all about what we're doing.
Okay, I'm real close.
That's okay. My name is Cheryl Harrison. I was a postdoc at NCAR in the ocean section. I am an assistant professor at the University of Texas, Rio Grande Valley, and I'm moving to Louisiana State University in Baton Rouge to the Department of Coastal Ocean and Coastal Science. Great, thank you. So, and I'm the FishMIP Earth System Model Coordinator. Next slide, please. So the outline for this talk is a motivation, what is FishMIP, talk about some background on marine ecosystem models or fisheries models, which we abbreviate as MEMS. We have results from CMIP 5 and CMIP 6, and a paper where we use CSM data exclusively, which is disentangling temperature and lower ecosystem drivers on marine ecosystems, and talk about some of the future work we're doing. Next slide, please. So FishMIP is part of the intersectoral impact model intercomparison project, which does a lot of work on agriculture and water resources. It's a consortium of over 40 marine ecosystem and fisheries modelers representing both regional and global models. We answer questions about the future of fish and fisheries, supply, marine biodiversity, marine ecosystem functioning. And the goal is to bring together disparate marine ecosystem models to help better understand and project the long-term impacts of climate change on fisheries and marine ecosystems, and to use our findings to help inform policy. And on the left is a schematic how these models work, which is we take Earth system model data to force these ecosystem models. The Earth system models resolve primary producers and zooplankton, which is a secondary producer, and then those are used to force these food web models, which vary greatly in how they're constructed. Next slide. Thank you, Ian. These are the coordinators currently for FishMIP. It's an international consortium. The current leader is Julia Blanchard from University of Tasmania, who is transitioning from Derek Tittensor, splits his time between Dalhousie and Cambridge. Previously, William Chung, Heike Lotze, and Eric Galbraith were coordinators. And you might recognize Colleen Petrick. Some of you are working with her on fishery stuff. Next slide, please. So one of the questions to answer is, how do we simulate marine ecosystems with Earth system models? Question, Keith Lindsay, a discussion Keith Lindsay and I had about this is that they're just not designed to do it. And I'm like, I think we could do it. And it turns out a lot of people are doing it. Of course, it's wrong. All models are wrong. But how do we do it? So here are two different kind of to think about how to do it. On the left is a kind of trophodynamic model that Charlie Stock did that has evolved into a different model, Feisty, that Colleen Petrick uses. And basically in that model on the left, you're dividing up fisheries into pelagic fish and demersal fish, which are on the bottom of the seafloor. And you take two different drivers for those, the zooplankton production and the detrital flux to the seafloor. And then there's some kind of transfer efficiency that says, how do we get from these food sources through a couple different phases of the food web to fish? And that transfer efficiency depends on temperature and other things. Another way to look at the models is through the size structure or the size classes. So we think about if we plot on the right, this is from a paper by Ryan Hennigan, one of the coordinators for FishMIP, who's a mathematical biologist. And if we plot body mass size class versus the abundance, there's a lot more small things than there are large things. And there's some transfer of energy or carbon biomass from small things to large things. And when they have babies, they make small things. And all of these have different kinds of rules associated with them in terms of growth and how they eat each other and how they reproduce. And that depends on temperature and how much food there is and lots of different things. These models are forced by net primary productivity, or the carbon fixation of primary producers, phytoplankton, or they're forced by biomass of phytoplankton or biomass of zooplankton. And we're gonna see that it matters a lot, what's forcing them, what the results are. Next slide, please. So how does climate change impact marine ecosystems? So this paper by Ryan is all about that through the lens of the size spectrum. And you can see we have the slope of the sizes, so body mass size versus abundance. And one of the things that we think happens with temperature change is that biomass goes down all over. And this is a physiological effect of cold-blooded species, how they work. We can also see this results in less large marine animals like fish and sharks. We also can see range shifts, changes in spawning timing, mismatches matches and predator-prey relationships. The zooplankton biomass is happening at a different time than when all the fish babies are happening, and so they starve. This is something that has happened to salmon species in the California current, for example. You also have things like coral bleaching, habitat, and for coastal species, sea level rise can be a big problem with that. And it's a complex nonlinear system, so you can expect that the unexpected will happen, and there will be weird cascades, and so lots to do. Okay, next slide, please. So this is a quick summary of the CMIP-5 fish MIPS results, and this is in a paper by Latza et al. 2019 in PNAS. And the title tells you the big take-home message here is that when you have climate change, you get a trophic amplification. Trophic amplification means that larger things feel the impact of climate change more than smaller things. So these plots A and B here on the bottom left are the change in the ecosystem biomass, so these larger animals, in the different RCPs. So we have on the bottom panel A, the historical is the black, and then it breaks into the 4 different research concentration pathways or carbon, CO2 in the atmosphere amounts. I'm sure most of you are very familiar with this. And then on the right is a breakdown of the different models. This study used 2 different sets of Earth system model input from the GFDL model and the IPSL model, and those were chosen because they spanned the climate sensitivity, the sea surface temperature change under RCP 8.5. So IPSL has doesn't get as hot, and GFDL got really hot, or maybe it was I think it was the opposite, vice versa. And there are 6 global marine ecosystem models. And so what we see here is a decreasing fish biomass over time. There's a large spread in the marine ecosystem models, and there's a significant difference between the resource concentration pathway RCPs. And so, yeah, next slide. So this is another set of figures from that paper. And so the left figure shows 4 different lines. Green is net primary productivity, and the dark green is phytoplankton, the yellow is zooplankton, and then the blue is fisheries. And what we can see here is as we have the RCPs, as there's more warming, more CO2, we get a decreasing in all those categories of the marine ecosystem, but we have a larger decrease in fish than we do in the lower trophic levels. So this is the trophic amplification. The bigger the organism, the more the impact. And one of the cool things, I think the coolest figure from the most interesting figure from this paper is if we plot the change in surface air temperature over all the RCPs, and the change in total biomass at the end of the century, it really plots out on this very straight line. And what we see from this is that there's a really strong relationship between temperature and fisheries decline. So you get a 5% decline in fisheries biomass globally for every 1 degree of warming. Next slide, please. Okay, so for CMIP-6, for those of you who haven't been following along, CMIP-6 in general are warmer, so there's higher climate sensitivity. This study is in review right now, and we're trying to get this into AR6 report and IPCC. And the take-home message here is you have more warming, you have more fisheries decline. And with some caveats about there's interesting changes in the drivers, but you can read the paper if you really want to know about that. Next slide, please. Again, so more warming, you have greater fisheries decline. So the solid lines here show CMIP-6, and the dashed, I guess they're kind of dotted lines, show CMIP-5. You can see for both 8.5 in red and 2.6 in blue, we have more fisheries decline than we did in CMIT 5. Next slide, please. Okay, so so the next paper I want to talk about is one that's also in review in progress in oceanography right now, and this is the driver decomposition. So it's kind of a brute force Taylor expansion, and the question we wanted to ask is, how do system models respond to changes in temperature and lower trophic level forcing? And so we just divided it up. We forced the models with the change in temperature, but kept the food source the same, and then it did the future change in food source and kept temperature the same, and then saw how they broke down. And I'll have a slide about the model design in a second. So just some background here to really think is ecology is not physics, and exceptions and species variation are the rule. You have a niche open up, you have that does a weird thing. And so there's many structural decisions to make. There's a question that I'm gonna, sorry, it popped up, it got distracted. I'll come back to that later. So there's many structural decisions to make and how to go from Earth system models to fish. And you know, you can think of that as like, oh, it's all wrong, but it's actually really interesting because these are well-informed decisions about how these biological equations work. And so that variation in how these models are constructed is actually really interesting. So the models do agree that there are direct metabolic temperature effects. If it's warmer, you have less biomass because they're, you know, cold-blooded animals. But there's a lot of uncertainties in the structure of the food web models, including the details of how these temperature impacts vary across different species groups, sizes, growth and metabolism, how to simulate the food transfer exactly, how climate change affects that transfer. And like I said before, they take two different various trophic level forcing, either the net primary productivity, which is this transfer by phytoplankton from inorganic to organic carbon, but fish don't eat phytoplankton, they eat other things. And so a lot of the fisheries models will take zooplankton biomass, for example, or some combination of zooplankton and phytoplankton biomass. And the important thing to note here is that primary productivity and biomass of plankton have very different spatio-temporal distributions. And I highlighted this in a recent paper where we were constructing a food source for baby turtles. You know, you can have a lot of primary production that doesn't translate into biomass sticking around. Next slide, please. Okay, so here's the model design. We're using CESM CMIT 5, and that was because I dug through the archive and found all of the files we needed, and we ran ecosystem models in the high emission scenario. Broke it down. We have a control experiment where we use the pre-industrial control for everything. And then we have a temperature change where we just change the temperature, and a lower trophic level change where we just change the lower trophic level drivers, whatever they are, leave everything the same, and then all climate change. And that all climate change also includes some of the models use oxygen or pH, and so it includes all those other drivers. So we can get kind of a residual, doesn't depend on this linear combination of temperature and food source for marine ecosystems. Next slide, please. This is a slide that shows the different drivers for the CESM single realization. That's the CMIT 5. And on the left are the levels of temperature, primary production, phytoplankton carbon, and zooplankton carbon in 1950 to 1960, so kind of pre-warming. And then on the right are the percent change. And so we can see that, for example, if you look at the bottom two right plots, they have very similar spatio-temporal distributions on the whole. But if we look at net primary production, which is the second, I wish I had a pointer right now. And can you point to panel D, please? Thank you. In panel D, we see the net primary production change, and it looks really different from the biomass change. And so shout out to Kristen Krumhart, who's on the call, that she has a really great paper talking about why this is. And one of the reasons is you have a more nutrient recycling, there's a shift to small phytoplankton diatom production, and that results in more recycling. So you just have really different, the biomass doesn't stick around in some of the shifts. Sorry, I'm not explaining this well, but you can go read Kristen's paper and she tells you all about it. Next, please. Okay, so this is a really busy slide. I'm my time here. I think I'm out of time. So so the take-home message here is that the temperature effects have really large uncertainty. So if you look at the first column, looking at the temperature change, it really, really varies between the models. And then the low level effects agree more, but it really depends on the driver, whether they're using mass or net primary productivity. Next slide, please. And again, if we look at the global integrals of those, we can see depending on the driver and the really large spread in the temperature change impacts. And then we have some residuals, which are pretty small except for one model. So mostly it's a linear combination of these two, the temperature and lower trophic level change. Next slide, please. So, this is just repeating what I just said. And so next slide, please, for sake of time. So other studies we have in the works for fish MIP is we're comparing the regional and global marine ecosystem models. They don't agree. And we're doing fishery scenario development to go with the SS. So how will fishing change in response to climate change? My lab is working on climate shocks to food supply. Kim Scher will be giving a talk this afternoon on fisheries impacts of nuclear in the climate variability and change group. And then FishMIP is open to collaborators. So we have all this data, we have all these runs, and we're really open for other people using them. So please contact us if you decided to do anything with this data. And that's the end of my talk. Sorry to go over time.
No problem, you started a little late. So I'm going to keep wrangling the slides here during questions. Frank, could you maybe watch the chat window? It's kind of hard for me to keep an eye on that.
There was a question from Claudia Wieners. Do you want to go ahead and ask your question, Claudia?
Yeah, so Claudia asked, suppose we would not warm the earth but cool it by a similar rate, what would that do to fisheries? Is the warming the problem, or rather the fact that the system changes ecosystem to adapt? Warming is the problem, changes in food supply. And if you cool it, you can come to Kim's talk because nuclear does cool it. And there are some scenarios that we do for nuclear winter, which are really similar to volcanic eruptions, which cool the planet. And it's interesting. It's a little different. So I'll refer that to there. And these ecosystems in these models don't really adapt. They're not that sophisticated, which might be one of the problems, is that we're not estimating, just that fish can't adapt to these changes in their habitat really quickly. But there's a lot to unpack there. So I would love to discuss it more with you. Thank you, Kyle.
Any other questions for Cheryl? I had a quick question. So I guess, as you're probably aware, Matt Long and Colleen and others are looking at coupling some of one or more of these fish models, Feisty in particular, I think, online with CESM. Do your results suggest that is necessary, or what
Yes.
advantage would there be to having an online coupled versus an offline driver scenario?
Ian, can you go back a slide? Yeah, so one of the kind of discussion points for this paper is there's no feedback between predators and lower trophic levels. So basically these fish have unlimited food supply when you force them offline. And so we're missing these key processes is that, you know, predation does change zooplankton, which changes phytoplankton, which changes biogeochemical cycling. And there's higher feeding rates are expected for warming. So yes, that will be very interesting and is important. Great question.
Okay, I'm not seeing any further questions. And
Thank you,
we're
Ian.
Sure.
6 minutes into our break. So I think we should go ahead and take a break. The call will stay open for anyone who wants to just hang out and chat and have your coffee. And we will resume at 10:20 with our more panel-like session on wind waves. So I'll see everybody then.
Thanks, Cheryl.
Hey, Cheryl.
Oh, hi.
Hi. Luann, I think we've met before.
Hi, Luann. Yeah, we
yeah.
were, you were my empowermenter.
Oh, that's right.
Yeah.
Way back when.
Yeah.
Couple of things. You know David Trossman?
Yeah.
Yeah.
We're writing a proposal together right now.
Yeah, that's fabulous. So I was just going to send an email to both of you to connect you, but he's moving to Baton Rouge too, which is so great that you're both starting out there.
Yeah, I think that we will get along well.
Yeah, he's great. He's great.
Yeah.
And then I also, I've been working with, Hillary Scannell just finished with me. Mm-hmm. And, you know, she works on marine heat waves. And so I've been thinking a lot about that. So I'm pretty interested in your work and this MEP too, because of, you know, the justification for studying marine heat waves is always fisheries. And yet I know nothing about fisheries. So I just wanted to make that connection because I think it's really important.
Yeah, and that's, you know, exactly the kind of thing, like if you had a student who wanted to interrogate these models, looking at marine heat waves that are resolved, it would be really cool to bring those physical forcings and their run, you know, so we have this data and we're really keen to share it and for cool stuff to come out of it.
Yeah. So anyway, I may be in touch. I have a new student starting on it. Unfortunately, Hillary graduated, so I don't have her anymore. But she developed a marine heat wave tracker to track them in space and time. And the first step of this project is to apply that to one of the large ensemble simulations, and then to because she's done it on OISST, but to see what we can see in the large ensemble and if it kind of works in a similar way or not.
Yeah, we've been, so I know you work with Elizabeth Maroon as well, I believe.
Yep.
And so we also work together on mocked as really weird things in nuclear winter. So we've been working and
there she is.
Yeah. So we've been talking about this North Atlantic, you know, the warming hole, and how that might impact fisheries. And I think we might have convinced some people to run some fisheries models on an ensemble, which has not been done. And so, so if people have ideas about that and have students who want to analyze that, like, I think we could talk people into running fisheries models on ensembles pretty easily.
Yeah, good. Well, we'll be in touch. Yeah.
Yeah, I want to jump in. Hi, everybody.
And Susan too. Yeah. She's our broader impact, but more than that. So
Yeah, I wanted, Cheryl, I mean, so many of the things you guys have just been saying, I would love to stay in the loop on. So marine heat waves have been known to kill off the eelgrass in the Chesapeake Bay estuary system, also in our back barrier system here in Virginia, probably elsewhere too. And so I have an interest in that. I don't know, Cheryl, if your ecosystem models have things other than fish in them, but I think that a connection could be made. I also have colleagues who are working in fisheries, and I'm currently part of a team looking at impacts of offshore wind, but part of that is detangling what's happening with offshore wind and climate change. And we're looking at the impacts on fisheries. And we've already seen, like, the summer flounder used to be off the coast of Virginia, and now our fishermen are having to go up to New England to catch the flounder. So anyway, I think there are a lot of connections that we can make here too. So I'd love if you guys kept me in the loop too.
absolutely. It would be fun to have a conversation.
Yeah. And we have various different tools. Like one of them is I think it's NOAA's coastal tool. And then I manage a coastal resilience tool where, like, you know, there could be actual application of some of the things that we learn.
Fabulous.
That sounds really cool, Susan. The Earth system model, like these global ones, don't resolve the coast well. The Earth system models don't resolve the coast well. And they don't resolve Chesapeake Bay for sure. But there are a lot of regional models, and we do have a lot of regional fisheries models in fish. And I can connect you with the people coordinating that. So if you go to the FishMIP website, Tyler Eddy, he's listed on there as the regional model coordinator. I'm sure there's fisheries models for the North Atlantic, like the East Coast. Yeah.
So your models,
I'm sure there's a number of them. Yeah. I don't know what they are off the top of my head, but I'm sure they exist.
So when you were talking about your models, where you took the data from the global climate models and put them into your, like, trophic models and things like that, that was still a global model?
Yeah, so those are global models, but there are a bunch of regional models, regional fisheries models that work in various ways. Yeah, and it would be great for you to connect with those people. So I would recommend, I'm happy to talk to you, but I would recommend talking to Tyler Eddy, who's up in Newfoundland. He's and Derek Tinswart is in Dalhousie. So they're on the coast as you, and with similar currents that are connecting you all. So
well, in the IHF data, the high resolution data just became available. So the 10 kilometers. It's still not.
It doesn't have biogeochemistry though.
No, it doesn't. But at least that is and it's 10 kilometers, so that it probably doesn't do the Chesapeake or Puget Sound very well. But at least there's going to be more physical variables available, sort of for the climate change simulations and stuff.
What about the newly released CSM2 large ensemble? Are there more BGC type variables available there?
I missed that talk yesterday because I expired after 6 hours of Zoom. I couldn't handle it anymore. Or Monday, yeah. I don't know. I bet what I know from CSM2 is turn ocean biogeochemistry off. In CSM1, you had to turn, and now it's hard to turn it off. So most of the things are running.
Large ensemble has the biogeochemistry on full.
Yeah, so there's a lot of fun things we can do with that. That's a rich data source to play around with. We're also, there's the couple of these high resolution kind of hindcast analyses. CSM has one, and GFDL has one, and we are FishMIP is planning to do. We have a couple papers we're trying to get out right now, but I think one of the next projects is to do high resolution fisheries model ensemble and see how that changes things, which will be really interesting. Yeah. Thanks
Well, I did,
for
well,
your
I did-
interest.
yeah, and I didn't think I'd get new connections by logging into a Zoom meeting. So there you go. I mean, I know you, Cheryl, but still to reestablish those connections, it's great.
Yeah, cool. This is great. Yeah, I mean, I'm happy to, as well. Yeah.
All right, I do have to step away, but it was good to see you all, and I'll be in touch.
Yeah, do. So, hi, Cheryl. Nice talk.
Hi, Laura. Thank you.
Hi. Yeah, we're doing some interesting work in Antarctica. It just made me think, and Kristen's really involved with that. But we're looking at like influence of polynyas and open water on predators and predator populations. And then Alice de Vivier just got a proposal funded to work with to start using the model and the biology and stuff to try to make recommendations for marine protected areas.
Oh, that's great. I would love to hear
It's
more about
really
that.
exciting. Yeah, it's really
Down
exciting.
in Antarctica?
Yep.
Marine protected areas in Antarctica?
Yep.
Yeah, that's really cool.
Although we have been warned that the science may or may not be taken into account when they make their decisions, but we're still going to go ahead and make some.
Yeah. I don't know what it's like in Antarctica, but like being from the California coast, you know, it's always a big fight between regulators and fisheries.
Yeah, and in Antarctica, it's just complicated because it's all these different countries as well. So each country gets to have all the, you know, it's just like,
oh my god,
or so I've heard. So we're still going to plod along, and also this idea that the best areas to protect might change in time. So as the climate changes, the area that you thought would provide the biggest benefit in protecting, that may change geographically.
That's really interesting. Yeah, that's really interesting. I feel like we need to have like a special session. I guess like ocean sciences just have like, you know, using Earth system models for marine ecosystems. Maybe there is going to be a session about this.
That would be a great.
It would be a really good thing to do.
Even just a chalk talk,
yeah.
Like what are we doing and what applications are we doing? Because I think the efforts are so kind of just individual little groups here and there that we often don't know what we're doing, and we're probably repeating ourselves in some ways.
Yeah, it'd be cool to have like a Gordon conference or like, you know, something like that. That would be really,
oh, wouldn't that be great? Or Chapman conference?
Great. Yeah, Chapman, Gordon, one of those. Yeah, we should do that. Let's do it, Laura.
Yeah, let's do it. Okay, we have to make a proposal. You're probably like have so much time you don't know how to spend it.
Yeah, right. No, I made a list today. I'm totally overwhelmed. I have mountains of boxes in my new house, and I have 5 papers we're writing, 3 like in actively writing, no 6, 3. It's just insane. Like it's
oh my gosh.
I was like, this is I'm totally overwhelmed. Yeah.
I bet. So are we? I think we're going to be kicked off here.
Okay. Fast, Laura. We're also making a lot of progress on that Antarctic ice nuclear war paper. We'll tell you about.
Oh, that would be interesting to see.
Yeah, Josh has been running a lot.
Which runs are you using, or which model were you using?
The CSM. It's the nuclear one.
I know, but the 2 or the 1? CSM 1 or CSM 2?
CSM 1.
Okay.
1.3 beta, whatever. Like
Yeah. Oh, that'll be interesting.
Yeah. Chuck's special CSM. Oh, I have to jump over to the Helio group, but it was really nice to see all you guys.
Okay, nice to see you too.
Okay, I think we should get going. It's great. People are able to connect like we were all drinking coffee out on the mezzanine in the Mesa Lab, and hopefully our winter group meeting, that will be the arrangement.
We do also have time at the end of this, as Frank said earlier, 30 minutes of open Zoom from 12 to 12:30.
Yeah, so please take advantage of that. All right, so we're now going to launch into a session on wind waves, and we've sort of set this up more like a panel discussion. So we have 5, 6 panelists Each will give about a 10 to 12 minute presentation on their perspective on where we should be going. And then my intention and hope is that those panelists will then lead the discussion, because they're the ones that know what the issues are and what the questions are and what the technical challenges are. So I'm hoping that they will help, or not help, but will carry that discussion forward. And once we've gotten through the talks too, we have, as an experiment, we have a Google Doc that we can use collectively to take notes, possibly start the beginnings of a white paper or a strategic plan as we feel necessary, that could then be shared on the OMWG webpage as sort of a marker of where we got to today, that people can look back at and refer to, and other groups working with Mom 6 can sort of see where we as a project are going with this. The last point is we very much want this to be an effort that benefits the entire Mom 6 developer community. We have some specific requirements and interest in CESM, but we definitely want to be working across the Mom 6 community. So we're going to start off with Baylor with a little bit of background and theory, I think. So Baylor, why don't you go ahead?
And that document can be found in the chat.
Right. Todd just put a link to the Google Doc there.
Sure. So, hello everybody. We've been messing around with waves in kind of an experimental context for a bunch of years. I wanted to talk about where it looks like things are headed now, which has a bunch of different complexities to think about. One key part is the wave-driven forcing itself. And the second part is how it breaks down by scale. So whatever, this is a nice movie of waves. So as lots of you have probably seen before, we've large eddy simulations, the kind that Peter Sullivan and Jim McWilliams really pioneered, can simulate the turbulence response to waves. And this is a nice example. The colors are temperature. The only large vertical velocities are shown here. So these are Langmuir windrows away from that temperature front in the center and a temperature front in the center. That's one of the features that you think about, is how you would have these small scale features. And over the course of time, Qing Li and other students in my group have really led an effort to show that we can significantly reduce the mixed layer depth biases in most seasons and most of the world by including that small scale mixing driven by waves. And it does more mixing, and it also does more entrainment into the mixed layer. I'll skip over that little flame effect. And then Qing has also shown that using WaveWatch may not be necessary if that's all we want to do, is to add that extra little bit of mixing. And he developed, in collaboration with Oyvind Breivik and Adrian Webb, who are really on the wave side of stuff, a statistical model. So what we call theory waves, which is just a prediction of what the wave field would be like in a model like WaveWatch without simulating the waves. And so you can see, if I can jump back and forth, the lower right-hand panel there is showing that the mixed layer depth is essentially almost indistinguishable between when we use the theory waves version and when we use the full WaveWatch. So those are some of the pieces we'd like to get as far as the turbulence mixing. And in the turbulent mixing case, it really comes down to this special term in the equations, the Stokes shear force, which arrives in the vertical equation, and it scales with this parameter epsilon over here. And what it does is when the Langmuir, the Lagrangian current and the Stokes drift are in the same direction, it exerts a downward force on the flow. Like that. And so It's a downward force, so it actually changes the hydrostatic balance. In that case, it's in the vertical momentum equation. And we've seen that on even larger scales at the submesoscale and mesoscale, large temperature fronts, such as this one that's from a large scale LES, actually you can see their effects, the effect of this Stokes shear force on the downward velocity. And so it looks like a Langmuir cell, one of these typical Langmuir cells out, but just a really big one. So apparently the same phenomena is happening on mesoscales and submesoscales as is happening in the Langmuir scale, but of course with different scales. So how do we understand that from the equation perspective? Oh, and this is the last aspect. So Sean Haney in his PhD thesis showed that it's really important to consider the so-called anti-Stokes effect, which is where the Eulerian current responds to oppose the Stokes drift. I'm not going to get into details of that, but Brodie Pearson wrote a very nice paper on how difficult it is to think about this and how even large eddy simulations are probably doing this effect a little bit wrong. Okay, so Nobu Suzuki and I thought a lot about this set of equations and how to make it simpler to understand. And one simple thing to do is, which was shown before by Daryl Holm, but we kind of wrote the equations in a cleaner, more approachable format, is just one way to think about this is that advection of everything, advection of momentum, advection of buoyancy, advection of salinity, advection of vorticity, or tilting of stretching of vorticity, advection of potential vorticity, advection of turbulent kinetic energy, can all be thought of as affected by the Lagrangian velocity. And that's one of the big effects of Lagrangian here is the Stokes plus Eulerian velocity. And then there are these other two forces you have to consider in the momentum budget, the Lagrangian Coriolis effect and the Stokes shear force, which I already mentioned. If you have those three effects, that's actually everything you need in a large eddy simulation. And we spent some extra time thinking about how you could do this in a climate model as well to get maybe those frontal acceleration pieces that I talked about, even in a high resolution climate model, which is ahead of what we're doing maybe now, but that's cool to have in something like MOM6. And then the other piece of the story is we can't really do this Lagrangian advection for everything unless we have the Lagrangian Coriolis force there present to make the correct anti-Stokes effect. A lot of groups have experimented with just adding Stokes drift on top of whatever the modeled velocity is, and then seeing what it does to things like surface drifters. That's actually dynamically incorrect, because what happens when you add in these Lagrangian Coriolis and Stokes shear forces is that it changes the velocity field, and then you have to reevaluate and go backwards to figure out what the advection is really doing to build this whole set consistently. Okay, so, but to the main point here. So this is the set of equations that Nobu and I studied. And so here's that Stokes shear force. So this is the normal Eulerian flow and not including wave effects. If we include the wave effects, it just makes a lot of Lagrangian velocities appear and the Stokes shear force appear. You can do some algebra and bing, 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 expand it out, then make the hydrostatic approximation. And this set at the bottom is totally consistent being included in a model like MOM6. And that would be easy to do. But when Brandon got inspired to put this into MOM6, he wanted to use the Stokes, the so-called vector invariant form of MOM6, which looks like this at the top. So it doesn't have an advection term. So it's not so obvious where you stick the U Lagrangians, but Daryl Holm had shown in the past, and then Nobu and I revisited to show that this is the correct form in that form, which if you expand out, then make the hydrostatic approximation, you get this big long equation. But and then here's the vertical momentum equation with both the Stokes-Bernoulli effect and the Stokes vortex force, which combine together to give you the same answer of the Stokes shear force being in a wavy hydrostatic balance. So the point here is that despite the fact that these two equations look quite different, they end up in the same place, even surviving making the hydrostatic approximation, even though the wavy hydrostatic model isn't really hydrostatic. It's got a wave impact in the vertical momentum equation. And the amount, I should have said, of how big this term is versus this term is what that epsilon parameter is really governing. So epsilon is a way of checking on that. And epsilon is typically pretty small for coarse resolution models, but it may be as big as or bigger than the Rossby number. And so we definitely are very concerned with things that are ageostrophic transports. So I guess equivalently, we should be thinking about things that are non-hydrostatic effects or wavy hydrostatic effects that are equivalent small tweaks to the model system, even at coarse resolution. Now, the last part of the math that I wanted to highlight here is whether we write it in the way that the vector invariant form or in the advection form, you'll note that these wave equations only appear in either linear terms, if you're kind of thinking about distributing them out, or in nonlinear terms with itself. So Stokes drift times Stokes drift. And in either case, whether it appears linear, in which case there's no scale to scale nonlinearity transfer, or Stokes times Stokes, Stokes drift actually is very persistent in time and space, typically many days and thousands of kilometers are the typical scale of Stokes drift, at least away from the coast. That's a large scale times a large scale correlation. And so when you think about it transferring from the large scale to other scales, it doesn't go very far. It actually can't jump very many wave numbers. So what this means is that we won't end up double counting if we are parameterizing small scale Stokes drift effects at the same time as resolving large scale Stokes drift effects. Those, we don't get a cross scale coupling the way you would with normal turbulence problems because of the way that the Stokes drift appears in these equations and the way that the wave averaged equations work themselves. Okay, I already said that. And then the last piece that I wanted to say is one thing that our group is working on is, so and we originally were using WaveWatch to get all of our wave information. And so it looked like this, where WaveWatch was talking with the coupler and being passed over to POP. We're presently now in development with a bunch of other groups, building a new OPSI cap to talk to the new OPSI mediator, which allows an upgrade of the version of WaveWatch, but also allows us to link up to MOM6. And we are about to be finished with doing a theory waves version, which replaces WaveWatch through this same new OPSI mediator system. And that will make it much cheaper. WaveWatch, at present, we're running at about 3 by 4 degrees resolution in CESM2. To go to 1 degree to match the wave grid to the ocean grid is about 60 times slower. And to go to the 10th degree to match the high resolution ocean model is about 60,000 times slower. Whereas the theory waves have a negligible cost at all resolutions. So we'd like to have that basically for efficiency, even though we know the accuracy will be lower. That's all I wanted to say. So if there are any questions.
Okay, I think what the plan was, we're gonna, unless there's a question that requires clarification, we'll ask those now, but we'll hold broader questions to the discussion after we've had each of the panelists speak. So let's move on. I think Brandon was, oh, no, wait, let's see. Yeah, Brandon, you're up next.
Thanks, Frank. I'm trying to do this through the web interface, so hopefully this is all working right. Please let me know if not. I can't tell if my video is even working.
Well, we've got your slides in
There we go.
presenter mode, and we see you. We
All
hear you.
right, I'm going to hit play now. Hopefully this is still work.
Looks
now
good.
I don't see the Zoom anymore, but all right. Do you see my mouse? No. Okay.
Oh, yeah, there
Well,
it is.
thanks.
I see it. Yeah.
All right, excellent. So thanks for the invitation to join your meeting this morning. For those of you who don't know me, I'm Brandon Reichel. I'm at GFDL. I've been working on incorporating some of these exact same Stokes drift effects that Baylor was just talking about in MOM6 for about a half decade now. I'm really excited that this is being undertaken by the CESM group now. So I'm excited to work with you guys on this. So I was just going to give a little bit of an overview about where we stand right now with what's in MOM6 and what's next in our plans. So I could probably skip through most of this, but just a basic introduction. What is Stokes drift? So Baylor showed the nice GIF image that shows these net translation of fluid particles as you follow wave orbitals. It gives you basically a vertically decaying current drift that's associated with the surface waves that can interact with the background, what we often call the Eulerian current, through these equations that Baylor was just showing. One way to calculate the Stokes drift is if you have a wave spectrum, you can use this equation given here at the bottom. The wave spectrum here is given by psi, wave number k, direction theta, frequency omega, and then the depth, of course, is z. You could use this relationship from the wave spectrum to get the Stokes drift, the horizontal components of the Stokes drift at some depth z. If you're not familiar with the concept of a wave spectrum, basically you could take a wave field, something like this image from a picture Steve Griffiths took a few years ago in the Southern Ocean. And you can decompose this wave field into the various direction and wave number, inverse wavelength components. So that's what's shown in this image here all the way on the right. This happens to be a 5-meter wave field with a wind velocity of a wind speed of 12 meters per second. The vector is shown by this blue arrow here. And you can see based on the contours where the wave energy happens to be concentrated in this instance. So you can actually see two different wave fields here. One that's about 10, maybe 15 degrees counterclockwise to the wind, and one the other direction clockwise to the wind. And the interesting thing about this, especially because these are happening at different wave numbers or wavelengths, is that we can have a turning of the Stokes drift with depth. So I'm going to come back to why that's relevant in a bit. Why is Stokes drift important in an ocean model? So there's kind of two different scales of how we think about this. Again, Baylor covered this very nicely. At small scales, the turbulence scales, we have significant enhancement of these vertical fluxes. So these are the large eddy simulations, again, Baylor was just talking about. So what I just wanted to show, these are some results from some specific LES run by Ching Li several years ago. Everything's identical in these two runs, except for one of these has Stokes drift and one doesn't. I'm using the same color bar here to show you the turbulent buoyancy flux. This is basically showing how much we're entraining the colder, heavier water from below the mix layer into the mix layer. And you can see significant enhancement in this run with the Stokes drift and basically this Langmuir turbulence phenomenon. And so we want to include these Langmuir turbulence effects in our vertical mixing parameterizations we're using in the model. We heard about that a little bit before the break. So this comes from a paper, probably most of the co-authors are on this talk. Ching led this back in 2019, comparing different schemes with Langmuir turbulence. This is a 1D simulation at Ocean Station Papa. Sorry, the x-axis is missing. This is about a year cycle. And this is just showing the evolution of buoyancy in the mix layer in a standard configuration. So this is just a standard KPP model through CV mix. And then these are three different Langmuir turbulence parameterizations, each of which has been kind of separately developed from large eddy simulation results. In this particular case, what you can see, so the red-blue color scale now in these three panels is the difference from this top B, top left B panel here. And you can see additional entrainment when we account for Langmuir turbulence in our parameterizations. And it's somewhat similar in this case between the three parameterizations. That's not always going to be the case. And I would highly recommend looking at this paper for a lot more details of the discussion of kind of the state of the science there. Anyways, more specific, what we have right now available in MOM6. MOM6 can use KPP and EPBL. EPBL's the boundary layer scheme we've been using at GFDL. Both of these already include some Langmuir turbulence options. So some of the schemes that Baylor was talking about in the work Ching had done, as well as then the work we've done in EPBL. This is just showing a particular snapshot of the boundary layer depth. So this is the summer in the Southern Hemisphere. This used to be a particularly problematic region in these models. We didn't get deep enough mixing for a variety of reasons, but one of these being missing the Langmuir turbulence effect. So from these two locations, I've just shown the median annual cycle of mixed layer depth, the model in black, and an Argo-based metric is in red. you can see we're starting to do a pretty good job of resolving the annual cycle here, including getting the depth in the summertime much more reasonable than perhaps it was. These other two, so unfortunately I haven't run this model without Langmuir. We've been pretty happy with what it's done for us. So it's been a while since I've run a simulation without, so I can't compare those directly. But with this metric here at the bottom, it's telling you how much we enhance the mechanical mixing due to the Langmuir turbulence parameterization. This is the specific year, 2018 in these runs. And so this is basically an enhancement over the mixing in the absence of Langmuir, somewhere between 10 and even up to 40% in some of these. So this is just the mechanical component. You also, of course, have convective mixing. So what's next here, of course, when we run more large eddy simulations, we might be coming up with new and improved mixing parameterizations. It's a bit of a maybe a moving target in that sense, but and Bill might talk a little bit about this, I think, next. And we also can I've been thinking about incorporating some of these higher order turbulent closure schemes, such as the second moment Meller-Yamada type schemes via Gotham. Then skipping ahead to the larger scales, so Baylor just spent a lot of time on this, so I can very briefly mention that one of the things we're trying to do is to be able to account for these effects on the actual model resolved scale physics. At the very large scales, maybe these terms don't do a whole lot, but it's best, as Baylor said, to keep all the dynamics consistent. We need to be able to make sure if we want to get the total Lagrangian advection, that we're accounting for things like Stokes-Coriolis and everything. And so the main point to see here, these are two sets of equation. One is the standard equations in MOM6 right now, the vector invariant form, which is important for MOM6 being a C-grid model. And then this is the hydrostatic relation 2. So this is the horizontal equation 1, horizontal momentum. 3 is our continuity equation in the generalized coordinate, and 4 would be basically a tracer equation. So theta would be the temperature, or salinity could be represented by S. And so we've been working on adding the Stokes drift via this Craig-Leibovich averaging procedure to these resolved scale terms. And I basically highlighted in red the same terms that Baylor had in yellow in his slides. And the point of this is to emphasize that we can actually distill this down to just needing to modify these specific terms in the model to get the right transports, as long as we're conscious of what our actual model velocity is. Then I'm not going to go into too much detail, but this seems to be kind of the cleanest way to do it without having to do too much in the model and taking advantage of using similar forms of the momentum equations. Finally, I want to get into some of the more technical sides of this conversation. So this is how we actually get Stokes drift into MOM6 from WaveWatch 3. As I mentioned, we can use formula like this to get the Stokes drift profile from the wave spectrum. What we really want is we want the Stokes drift averaged over a layer. So we need to then be integrating this over the layer depth to get the total transport and then convert that into an average. The full spectrum, usually a WaveWatch simulation, does something like 25 wave numbers in 24 directions. That's a lot of information to be saving or passing back and forth. Now, we only need 2 directions, the X and Y, so we can collapse this down to about 50 components. That's still quite a bit. So the strategy we've taken is to reduce this from 25 wave numbers to what I'm calling here N wave numbers. So N could be, any integer between 1 and 25, basically. And this isn't an exact relationship that can be derived from this, but it's more of a parameterization using the idea of a monochromatic spectrum where we have a surface velocity and some decay scale K associated with that particular surface velocity. The advantages of taking this approach is that we can make N much less than 25 and still closely mimic having the full spectrum. This exponential form lends pretty well to what I call here semi-analytically evaluating terms, so we can do derivatives and integrals quite readily over exponential functions, which is nice for implementing this in a model. And with N being a relatively modest amount, I'll show this on the next slide, we can basically capture the broadband effects pretty well. So to answer the question, how many N's do we really need? This is one particular case here. This is from the Southern Ocean in a JRA forced simulation. The surface Stokes drift is about 20 meters per second. So black is the solution you'd get with the full spectrum. And then I've taken a number of values of N here. So moving from dark red to dark blue, where we have very few to a lot of numbers N. Forgetting the magnitude, which is the left profile here, turns out we probably need something like at least 3 of these, Stokes bands, basically. This happens to be a case where the Stokes drift turns a lot in depth. And with only 3 components, we don't quite capture that at the deepest part. So maybe you need to go a little bit more if you want to capture that depth dependence of the directionality of the Stokes drift. But the point is we can collapse this down now to something like 6 to 12 components versus 50, which is, a nice improvement, whether you're saving or passing these through a coupler. And then finally, just a quick recap of what we've done for using Stokes drift in MOM6 without a wave model. So we can ingest these surface Stokes bands from WaveWatch 3 output files. This is already in the wave model, the latest versions of the wave model. So being able to use the latest version in CESM will be important to take advantage of that type of infrastructure. This is kind of good for a one-way type simulation where you have a prescribed atmosphere. Within EPBL and KPP, we already can use this theory wave that Baylor just talked about to predict the Langmuir number, which gives us the Langmuir turbulence effect on the mixing. This is good for climate models where we don't have the resources to run a wave model. And then Baylor just mentioned a bit about the potential for using theory waves then to actually get Stokes drift profiles. I guess that's quite a bit more of a research question in how well that's going to work, and perhaps there's other simpler approaches. And so this is just showing, some of these ideas for how we get the Stokes drift into MOM6, whether it's that one-way sort of storing net CDFs, two-way coupling, whichever cap you happen to use. These are at varying instances of completeness, I guess. And then this is something that's maybe more, I guess, it sounds like Baylor's actually pretty close on this. So yeah, that's all I have. I look forward to the discussion and the rest of the talks now in this session.
Okay, great, thanks, Brandon. All right, move on to Bill Large.
Okay. Is the screen shared yet?
Not yet.
Not yet.
I pressed shared screen a couple times and I don't see anything happening.
So Bill, you gotta hit share screen. You gotta select what screen you want to share, either the whole screen or a certain window.
That might do it. That's what I thought I was doing. But anyway, share screen. There, you got it now?
There we go. Yep. There we go.
I'm pushing the same buttons. Okay, so I'm going to just follow up on what I interpreted much of the discussions that you've just heard over the last month or so. That's about all we've been talking about this a lot. The idea is to develop surface waves in CESM version of MOM6. And what we need to do today is to develop around a 6-month initial implementation plan. The goal is to enable research on surface wave effects and parameterizations. The thinking being when you hear all the different uses that these models are being put to in coupled mode, some of us are quite worried that the applications are outstripping the physics that's gone into it. And model development needs to continue if we're going to keep using it in all these various and sundry ways, which, we want to have some confidence that those are the best answers we can get. So the strategy we have right now is to follow the GFDL implementation that you've just seen, which is on a C grid, as Brandon mentioned, of staggered T, U, and V points. And the purpose of this particular report I'm doing now is just to go over the current status as a basis for the discussion that we started at 11:20 this afternoon. So nothing's etched in stone, and therefore that's a perfect time for this discussion. But here's where we are now, and that's a good basis to start with. Okay, so the topics I will talk about quickly is some of the ocean wave coupling details on what we're planning to do. I've underlined Alper Altuntas, who, as Frank mentioned earlier, will talk about this wave, what we've done with WaveWatch 3 at the beginning of the discussion, and it answers Brandon's question of what what we're doing on that and these recent versions and things. Then there's just talking about the momentum equations. That's what Baylor's been talking about. And Brandon, to some extent, contributions have been received from Jim McWilliams and Peter Sullivan. And then someone on the numerics, mostly coming from Bob Hallberg, with conversations with Brandon, Marcus, and Alper, and Ching Li. Just quickly, the experiments we now have, Gustavo actually went in and got enough computing time to run a number of single GRA cycles through 2018 as at least the beginning of an experimental framework of how we might test these various numerics that we're putting in to make sure that it's available for people to do their research on these wave effects. So the premise we have is that there will only be one-way ocean coupling to a hierarchy of ocean waves. You've heard something about the Wave Watch 3. There's also heard theory waves or statistical waves. We also used to have data models, but I'm not so sure that the theory wave might just take the place of the data waves. But it's one-way coupling, and we need to discuss this hierarchy. Which of these options should we focus on to get into the MOM6 version of CESM3? The wave model, as you just saw, will actually go or send to the coupler or mediator on the wave grid the stoke drift component that Brandon talked about, where he told me N was going to be about 6, as you saw. Now the difference, okay, so we will send those. And now there's the question of what are the other requirements. That's part of the discussion. Nikki talked about what you might need for bubble gas fluxes. So in general, there's wave dependent air sea flux requirements. What other requirements? We have some legacy stuff to think about. How much do we keep bringing in from before? So that's open for discussion. But what I would think about, who's actually going to do it? Who's going to provide the scientific guidance and justification for any requirements you might want? So watch it. You may be volunteering yourself if you step up and say you want something. The mediator coupler, as we said, it's on a staggered C grid shown on the right. So it will interpolate to these MOM6 horizontal tracer points at the middle, because right now that's where the vertical mixing schemes operate. Okay, so that would happen in the mediator coupler as far as we're thinking now. And then MOM6 on a time evolving spatially variable vertical grid, that's possible in MOM6 with this spatial variability of the grid. These are the Stokes profiles that Brandon mentioned down here, and the Lagrangian are just the sum, as you've heard. But one thing I did notice 2 weeks ago when I asked Brandon, this decay scale was fixed. It wasn't a function of the particular monoclinic wave component. And in his code, he's got that with an index. So whatever it is, it's only one more parameter. I'm not sure where Brandon is on that. But whatever it is, we can accommodate. And that's the plan, to stay as close to whatever he's coming up with, at least for this initial implementation, to allow people to get started on these experiments that they might want to do. As far as the momentum equations are concerned, the premise is that our vertical resolutions will approach a meter or better. Ultimately, we'd like to really just get a nice diurnal cycle of the diurnal heating layers just off the board, just resolved. So I didn't hear anything on Baylor on what vertical resolution. So I hope the discussion brings up what does this vertical resolution mean? And a basic premise is that, as you saw, parameterizations are going to be based on LES to a large degree, because we just don't have turbulence measurements of fluxes in the ocean. So that's going to require, one would think, MOM6 to solve a form of the same wave average Boussingault equations that you've just been looking at. So right now, if we're putting these parameterizations based on LES into a model that doesn't solve the same equations, you're not sure you're going to, well, you're pretty sure you're not going to get the same mean fields that you parameterize with and therefore the parameterizations are less certain. Your uncertainty rises. So that's the hope, that these with these new equations that you are new terms in the equations you've seen, we'll start getting the flow representative in the GCM that we get in the LAS. The additional Stokes terms you've heard, and boy, I tell you, you can move these things around. And thank you, Baylor, for sorting out a lot of the controversy on. Make sure you're talking about the same equations when you start talking about what term you've got. So you've seen all those, and we'll just take what Brandon's done to start with. And then we'll start talking about the vertical flux of horizontal momentum. That's the stress vector or minus the stress vector. And one of the things thinking at the moment is that the stress and shear vectors will no longer need to be aligned. In other words, we won't have down gradient viscosity baked into the solution. So I'll spend some time on that particular problem. The evidence for that comes from observations of ocean shear that I'm showing here, where one might assume that at the surface, and all the theory will tell you that, and everything, all the evidence I have, is that the wind, the shear, and the stress vector are all pretty much aligned at the surface. But if you look at this plot over here of the actual shear aligned with the wind, this is relative to the wind, this is downwind, this is crosswind, that at this point over here, it's very much downwind, but it's not zero in the crosswind. And so that means that the shear, I'm just guessing maybe 40 degrees to the right of the wind in this case at 4 meters at 2 p.m. If you go later in this observational record, this is from 15 North from Hughes et al. And these are rare observations, I must say. But if you look at 6 p.m. at 14 meters down here, there's an awful lot of purple, i.e. negative, and not so much red. So maybe you're 80 degrees off. And the thought is, what the heck's the stress vector doing? We don't have measurements of the stress vector. So we have to guess. And what we've been saying is that the stress is aligned with the shear. That's down gradient viscosity. Well, if the shear is, if this direction of the shear is only this scale, how would any motions and those big eddy motions you've seen know about just that scale when they're coming from above? So it's not at all obvious that the stress and shear are aligned when the stress vector, the shear vector has such small vertical scales. And that's just some observations we have. And we've seen other places of observations where there's small vertical scales of shear. So how would a stress vector made up of multiple scales, integral of multiple scales, just know about the local? So that's the evidence for why we would do that. Then we got into the discussion, well, what would we do? How would we actually compute the momentum flux divergence? Okay, well, right now, the plan is based mostly on Bob Hallberg. Thank you, Bob. That he says that the current implicit shear oriented with some possible wave enhanced viscosity that you've just heard about will stabilize the solution. So that will give you U and V at various depths K at n+1 or an update at U points and V points. And then the hope is that you can put an explicit wave enhanced inducement, induced enhancements from waves at the U points. You can do it explicitly, which this is so good. I mean, trying to figure out how to do this implicitly was a bit of a nightmare. And it is just almost too good to be true if this works. And the idea is to at least try, just put these increments in and just increment these updates that you've made implicitly and put these explicit wave-induced enhancements. So that means your mixing scheme, whatever it happens to be, as we've seen, might actually give you wave-enhanced viscosities and diffusivities, but then it could, I'm just a little too sensitive here, then you have to give it some of these wave-induced increments, all right? And so that's the plan at the moment. And so then what we have to do is we have to come up with some priority modifications that we have to do to the code and these mixing schemes. So if we want to, that's what we need to do today, if we can, or get as far as we can. Try find some high, medium, and low modifications, and perhaps even dedicate, saying things that might be possible, but it's just too premature, and give them a 0. So a preliminary stab at that, just to get started, is to parameterize the interfacial stress as a magnitude and direction for components, so that you don't have to have the down gradient or down stress and shear align. So your components might be, these are the increments. Now, this is what you want, and what you take away explicitly is similar to what the code will put in implicitly in that implicit viscosity time step, so that you actually get almost what you want, but you're using that implicit step to keep stable, and that's the hope. Okay, and I really like to see that. Why to do this and why it's a high priority is we look at some LES angles from the wind. This is a plot I have from one set. There's many other LES, and we should look at many, many more of these, which is why we want to put this in place. But that is the direction of the shear on the vertical axis from the wind, and the stress is on the x-axis. And the 1-to-1 line is not a very good fit. So the shear and stress in this particular examples are well over 90 degrees from the stress. So assuming that the shear and the stress are aligned is not a particularly good assumption. And given that we spend so much time trying to get the surface stress, i.e. the wind stress right, maybe we should put some attention into actually distributing the vertical a little bit better. If you look along this line, if that is basically assuming that the stress and wind align, all these points would fall along here. And that's not particularly good either. But clearly the stress tends to stay more aligned with the wind than the shear does, at least in this one example. And we need many more to see whether, what to do about this, hence some of this infrastructure building, to see whether any of this is even important. Another priority would be to put the default capability enhanced K and M, these diffusivities and viscosity independently. That's already done, or at least I don't think they're independent yet, but you can enhance the viscosity and diffusivity, but that is should go with updating the shape function, at least in our KPP version, because that reduces these coefficients in the lower boundary layer, not the upper boundary layer. And so they should probably go together to try and get these counter effects at least more aligned with what the LAS are showing. As far as going below the boundary layer, that's pretty premature now, though I know Kelvin Richards has always said there's lots of shear at small scale down there. That's where this would come in. And there's also some thinking that things depend on time history. Well, that's premature too. As I say, we're not sure that once these models get these different equations, whether they'll even produce anything hugely different or whether it matters. And that's the first thing we need to find out. There's also, which might be a low priority in my view, from the evidence I have, is to reformulate the HPL calculation to make it go deeper, if you have the right flow. Now, clearly what you've seen before, that it's been reformulated to give you deeper mixing with the old equations. What do we need with these new additional terms in the momentum equations? And that evidence that I have is this is just straight our current version using LES meets. I mean, that's the key. And you can see relative to what I can get from looking at the turbulence itself, which we don't have in MOM6, it's not a bad fit. There's only one period of time, and this is a very weird part of a diurnal cycle, the night after, where there's just no buoyancy flux, where there's a deviation. But basically, that's why this is pretty low priority. It is low, relatively good fit, whether you put waves in or you actually have a calm case. So I can't quite argue that that should be even a medium priority thing to do. Others may have other evidence, and that's what we need to see. What evidence do we have on what to go and start modifying? So that's all I have to say until, I hope, the discussion at 11:20.
Great, Paul. That was excellent. Okay, next up we have Cece.
Great. Right. Well, thanks for inviting me to speak in the Ocean Working Group. I think I've done this maybe once before, so I wish I had thrown in more equations to fit in better. I want to start by thanking my co-authors, especially Letty Roach. The others are listed here, have all been really instrumental in this work. This figure really is my motivation to start with, that shows the sea ice edge in the Southern Ocean. And you see this incredibly beautiful structure of eddies and a gradient in the, I would say, quality or fuzziness, but that really is so, I think, fine structured that we are seeing it as fuzzy, but what it really would look like are flows on the scale of a meter at the ice edge. And then these kind of interesting transitions to maybe even a somewhat abrupt to a much larger flow regime. And why would we care about flows? Well, sea ice modelers would care because they influence strongly the, I'll go back to this, perimeter of flows and the ice-ocean lateral interface, and therefore the ice albedo feedback. But we don't have a lot of real detailed evidence of that, but this figure I think is kind of cool, showing when we've composited waves on occasions of high ice extent events, so 5-day kind of events of extreme ice. What we see are waves tend to be propagating away from the ice, as well as having lower wave energies. So if you think about the opposite of this, you would expect when the sea ice retreats to have waves propagating towards the ice and higher wave energy. So there just appears to be some empirical evidence for a relationship. So the other factors maybe for you are that as you expect waves to be propagating into the sea ice beyond the ice edge, there should be some effect on the ocean in the presence of sea ice that currently we're not capturing in the version of WaveWatch that's in CESM2 for two reasons. One, there is no Arctic in that grid, but where there is sea ice in the subpolar oceans, the waves are assumed not to propagate into the sea ice, and there's no wave energy introduced into the ocean in the presence of ice. So no wind waves created in the presence of ice. So I'm interested in changing that with these motivations for many reasons, sea ice modeling as well as ocean modeling. And I already mentioned that smaller flows, really, really small flows, especially at the sea ice edge, have a much greater perimeter. And so, yeah, these are points I already made, except for the last one, which is how sea ice model, the CEIS-5 model, currently treats flows as they're all the same diameter and they're 300 meters in diameter. And this basically puts us in a very weak ice albedo feedback regime for many lateral melt. Lateral melt is very, very modest in that model because the perimeter is very small. When reality is that I've shown you pictures of the ice edge, but also analyses of those kinds of images have shown that the distribution of flows by number here maximizes, of course, as you get smaller and smaller. They're just semi logarithmic in this diagram, or power law like in this diagram, and that basically means that the majority of flows are small, right? And we're treating them all as 300 meters, which is here on this scale. So it depends on where you are. There may be no flows that are even 300 meters in diameter. So we started to model a flow size distribution in CEIS, and we had always modeled the sea ice thickness distribution. So we have a history of modeling a distribution already. And this is that thickness distribution. So we look in the model, we treat 5 categories of thickness and an open water category as well in a probability density function at every grid cell. So it's kind of a subgrid scale parameterization, but with a method for allowing redistribution among categories when there's ice deformation or thickness and growth. Thickness, growth and melt. But now we've added a second dimension to that distribution. So here's the thickness, and now we've got a horizontal dimension here of flow size. And so we're treating it as a joint distribution. And of course, the variation in flow size is harder to see because it's spanning this wide range of scales. But if we looked in detail, we would see that it is thickness dependent. And so it is important to treat it as a joint distribution. So we've coded this up. We've been doing this for 4 or 5 years now. I just want to briefly explain kind of the main important processes for this distribution, flow size distribution that has 2 dependent variables, size and thickness, is a transport, thermodynamic effects, deformation, ridging, rafting effects, and wave fracture. This is the biggie that really affects flows dramatically in size by fracturing them in the presence of waves. And waves are incredibly effective at fracturing sea ice, even fairly small waves. But the thing that actually changes the concentration of ice is just lateral melt and lateral growth. So the feedbacks on ice albedo feedback, or the influence on ice albedo feedback comes in through the thermodynamics, but we really need wave fracture to create the small flows that have a lot of lateral melt. So just how this is done is to imagine a big sheet of ice and a wave propagates in and starts to deform that ice in the vertical, if you like, and where the peaks and troughs will span a flow, you would expect fracturing. So fracturing here, wherever there's either 2 highs and a low or 2 lows and a high. And so what we do is take from WaveWatch 3 the wave energy spectrum in 1 dimension and convert it to a hypothetical flow, surface height field, and then look for the lengths of these separations between troughs and peaks. And then where those occur, if the curvature of the sea surface height is sufficient to fracture the ice, we obliterate it. And I'm telling you, it's incredibly good at obliterating ice. So then how sea ice in turn influences waves is where wind energy is introduced into the surface wave model is scaled by the open water fraction. And that's irrespective of the wavelength. So for all frequency of waves, they're treated the same way. And I'm going to come back to this point in a minute, but the other way is through propagation. So waves propagate into the ice and they're damped as they propagate in due to scattering, as well as what is thought to be some kind of viscous damping from the actual deformation of the ice in the wave field. And we treat this as a function of ice fraction, ice thickness, and flow diameter now in WaveWatch 3. So this is something we implemented in WaveWatch 3 based on a theoretical model and some observational empirical fits that were created in collaboration with Mike Malon. So just briefly, a little bit of results to show you that this looks like it is important. We've been implementing, doing experiments and a series of publications and now testing. And I'm going to actually present this kind of intermediate level where we've done most of our work, and that is with just sea ice and ocean waves coupled. So we don't have an active atmosphere. Instead, we're prescribing atmospheric reanalysis. And nor do I have the ability to show you directly how it influences the ocean, but I can show you how we think it might. We're currently testing a fully coupled model, but I don't have any results from that to share. Just to give you the drama first, in the Southern Ocean where surface waves are greatest, near the ice edge, they do certainly propagate into the ice, especially in summer in the Southern Ocean where winds are still very strong and surface waves are still quite large. We are seeing significant wave heights in the range of 1 to 2 meters within the sea ice edge. This should have labeled, this is the 15% sea ice concentration contour. In the marginal ice zone, the dotted line is 85% sea ice concentration. We're seeing substantial wave energies. Of course, this depends on our parameterization, which you may question. The concentration of sea ice is so much higher in winter, and the gradient of the ice edge is much more compact. So you don't see as great a region of large significant wave heights in the sea ice zone just because the marginal ice zone is smaller. The last result I'll share, second to the last result, is how this looks in terms of sea ice flow perimeter. And this is per square kilometer. Remember, without resolving flows, I told you all flows were 300 meters in diameters, which essentially looks like you would see any color, but it'd be basically black on this scale for perimeter. So once we start to resolve flows, we really, really substantially increase the flow perimeter. And in turn, the amount of melt that occurs because of ice albedo feedback is greater. And that ice edge tends to retreat in the Arctic, and just overall in the Antarctic, you see, because the sea ice concentration is already so low in summer, it looks like a reduction everywhere. So lastly, just to share how we think these waves are in the sea ice compared to observations of surface waves from moorings in the sea ice. We have a couple of different data sets from buoys, moorings here that I'm going to compare with. And just looking at the distribution of wave heights here as a probability density in the moorings in blue and the model in red. We have much greater, of course, number of observations taken in the model. So we have high confidence in this distribution in the model. What we see is that the model tends to exaggerate the significant wave heights compared to the moorings, which is also confirmed by another analysis of the non-dimensional wave energy versus the peak frequency when we look at the spectrum entering into the waves, into the sea ice. We see the model tends to exaggerate swell waves and emphasize the shorter frequency, higher frequency, shorter wavelength wind waves. So we think that there's a deficit of wind energy being introduced in the presence of sea ice due to that scaling I mentioned of just decreasing the introduction of energy by the open water fraction. So with that, I think I can't really tell what time I'm at, maybe a little bit over. So I think I'll just stop with my conclusions and take questions.
Okay, thanks, Cece. We'll take questions during the broader discussion in a few minutes. We're almost through our talks. So, Melissa, you're up.
All right, let me do my screen share. All right, does that show up full screen for you guys?
Yep, good.
So I'm Melissa Moulton, kind of new to this community. So to introduce myself, I sit in the ocean section at NCAR, and I'm also affiliated with the University of Washington through both the Applied Physics Lab and the Civil and Environmental Engineering Department. And my background's in coastal physical oceanography, but at really small scales, like in this picture. These are sensors I deployed, and I use observations like this and models to look at processes and hazards in this zone. Things like rip currents that people would encounter on a sunny day at the beach, and then also things like in this picture during extreme events, wave breaking, resulting currents and erosion. So I'm talking here, I think, as a little bit of an outsider to give a sense of, one of our topics that Frank suggested was brainstorming about research opportunities that these new wave coupling capabilities may enable. So one area is the coastal region. So, I'll talk a little bit, and I think everyone will agree that there's a ton of interesting topics at this intersection of climate and coasts and human impacts. But it's hard to bridge these scales, and resolution and what processes are actually represented really limit what can be done. And so I'll give a few thoughts to start discussion on, what we can do and how in terms of using this global information to look at impacts on much smaller scales. So first, in terms of scales, it can be helpful to point out that there really is a huge range of scales involved with coastal processes, and I've tended to work kind of in this orange zone, and it's really interesting to think about how we can bridge this really wide range of scales, including spatial scales that aren't even shown here in terms of global estimates, and then these long time scales over which humans are really influencing both climate and our coastlines. So to start out, just motivating why we study these coastal regions, and also to point out why sometimes we do really need to resolve these small scale processes in the coastal region. I just wanted to bring up one thing I'm working on at NCAR, which is trying to understand coastal flooding resulting from tropical cyclones, and in particular, high precipitation events where you have combined effects of precipitation and storm surge, and waves are a pretty important part of storm surge, and a factor that I'm thinking about is not only the flooding of homes, but also the flooding of infrastructure and how that can release contaminants to the environment and have big impacts on human health and coastal ecosystems. So here, to estimate storm surge in these really complex environments that are kind of bridging between the worlds of hydrology and oceanography, you actually have to go down to meter scales to get to estimate this flooding with reasonable accuracy. And a difficulty there, given how high resolution those simulations need to be, is that we often need to use ensemble approaches to get at uncertainty, for example, associated with different sea level scenarios or wave climate scenarios. But including waves is pretty expensive, as many of you know and have mentioned. Waves contribute a smaller fraction, but important fraction to surge, but can be kind of the most expensive part of these kinds of simulations. And so a lot of the research in this field can center around approaches to improve computational efficiency and kind of bridge these regions. So I show pictures like this to point out that, point out the obvious, that with CESM, we're not attempting to reproduce this kind of work in the coastal region. And I think the question is, what can we do with waves in CESM to inform these kinds of important topics? So what can we do well at a global scale? And so I'm not an expert on this, but from some digging around, I was surprised that these global scale wave simulations actually can reproduce wave heights at coastal moorings with reasonable accuracy. For example, this is E3SM with WaveWatch 3 with different types of grids, but the point is that you can get kind of reasonable errors in coastal wave heights, although coastal impacts might be more likely to go as wave height squared with the wave energy. But still, I think this kind of information can be good enough to address questions like how much energy reaches the shelf, for example, under different emission scenarios, and that can include kind of integrating over a number of storm events and other things. So that's good. I think that's a clear example of how even at the global scale we can say something about waves that are incident on a coastline. But these locations I would still call offshore as a coastal oceanographer, and a whole lot happens between those offshore moorings and the coast where these actual impacts happen, where waves interact with infrastructure or people that are at the coast. And so here's kind of a quick schematic of one way I think about this. And this isn't meant to be to scale, but these red dots could represent wave information and other information from maybe a 30-kilometer global climate scale simulation. And previous slide showed you can actually get pretty good information about how the wave climate and other factors might be changing here. But there is quite a bit that happens between there and the coastline that influences what the actual impacts are. So I tend to think of, that we need work to think about how to effectively downscale this information to the impacts via inclusion of things like, interaction with bathymetry, ice, vegetation, and other factors. And then also characteristics of the coastline itself that affect whether flooding occurs and erosion and topics like that. And then I also wanted to point out that, there are places that maybe aren't included yet where these coastal impacts can feed back to climate. Some have been mentioned tangentially, things like, if you have erosion of a permafrost coast or melting of landmass ice or things like that. So briefly, I just wanted to show a couple examples of where you really need to consider what's going on in this region between where the global scales are, global simulations are resolving this information and where the actual impacts occur. One that I wanted to bring up is, more of a polar topic, but since that's the place where wave climate is changing most dramatically, I think that's a place where there's a big opportunity for new coastal collaborations here. And I won't go into detail, but this picture shows landfast ice on a coast in northern Alaska. And the point is that, these global scale wave models can tell us something about the wave energy out here. And it actually tells us something pretty decent about the wave energy pretty close to the coast, except, in places where these moorings are really deep in this ice, where the coast is then completely protected. So this is a case where, taking this offshore information alone would not tell you which part of this coastline was going to erode. Other examples of how we can maybe downscale information, I think, include a lot of very reduced complexity models to be able to do the kinds of ensemble type approaches. We can't simulate in detail things like coastal morphologic change, but there's been lots of work done on how to parameterize those effects. And that tends to be, using kind of simple geometries and things like that. But for example, you could take wave information and sea level information and then relate that to expected shoreline changes on a global scale. There's many other examples, including coastal flooding, Arctic coastal erosion topics, barrier island migration. And a common theme is that these are really quite reduced complexity models in order to be able to address changes on long timescales and across different regions. The last topic I wanted to mention as a discussion point is, to what extent can, I mentioned kind of these reduced complexity models and using our CESM output as kind of a boundary condition on coastal models, but to what extent can we more directly use regional configurations or even global simulations at ultra high resolution like IHESP or something, that include waves to address actual coastal topics. And one example here is a recent regional MOM6 configuration, and here's the team here working on this, that's being used to address reef restoration, in particular using trajectories derived from these models to assess which reefs are most important to protect and restore. And so, these capabilities are really exciting, and there can be power in using doing this nesting in the same code base, as global models, where you can look at influence of things like ENSO or other things on these patterns. And then there's added power if we could couple with waves, because we could then include effects of Stokes drift and the associated Eulerian return currents on trajectories. Still, I would argue that these models are not resolving well a very important factor in terms of these connectivity estimates, which is how the larvae actually get to and from the beach. And so I think even in these nice super high resolution configurations, there's always going to be a point at which we're not resolving some of these smallest scales of coastal processes, which may or may not be important for the topic of interest. And so some of the things I'm working on are ways of using other modeling tools to parameterize those impacts better in studies like the one that I just showed. So that was it. And I think it's interesting to brainstorm how these things can be used, but I thought that it'll be really interesting to just see when these products are out there, how coastal oceanographers pick up these tools, what aspects they trust for their problems, and where that goes.
Okay, great. Thanks, Melissa. All right, we're gonna wrap up the presentations with a short presentation from Alper, just showing us where we stand today with in the CESM framework with MOM6 and WaveWatch 3 and timings and so on. So Alper, we're not hearing you, Alper. Doesn't show you muted.
Does it work?
Yep. Oh, we had you for a second and we lost you again. No, we don't have you. No audio. We can see you, no audio.
Opera, do you have a microphone in your machine? Maybe try unplugging it from your machine and plugging it back in, or just use your machine microphone.
It's frozen.
It looks like
Yes.
it's frozen completely.
Okay, let me see. I have Alper's slide here somewhere. I did. Let me. That was in an email yesterday. Sorry for the hold up. Okay. I will slide up. Hopefully, Alper can at least find some audio connection. See that?
So it looks like he's in here, but he hasn't joined in the audio yet. I'm not sure if that was from earlier, if he just joined.
Okay, I can't see the Zoom windows now that I'm sharing, but
Oh,
can you hear me now?
yeah, okay. I have your slide up, Alper.
Awesome. So sorry for that. I have this single slide summarizing where we are in terms of coupling MOM6 and WaveWatch 3 in CESM. So we just recently added this new WaveWatch 3 version into CESM. This is version 6.07. And so this new version currently coexists with the old legacy WaveWatch 3 that we have. The new one is optional, but it will replace the legacy version that we have once we finalize the development version. And the new version, this new implementation brings in many bug fixes and software improvements. And it also has these routines for the partitioned Stokes drift computation that Brandon described earlier. And also it has these ice wave coupling changes from Helen, Letty, and Cici. Cici described these coupling changes. And so as for this new version, we've coupled this with both POP2 and MOM6 and validated the POP2 coupling by running a JRA simulation. And we pretty much get the same boundary layer depths when we compare the old WaveWatch 3 versus the new WaveWatch 3 coupled with POP2. And we've added 2 new grids, the 1 degree POP grid and the 0.6 degree tripolar MOM6 grid. We can run WaveWatch 3 on these grids now, in addition to the legacy WaveWatch 3 grid, which I think is 3 or 4 degree. And so we've also added the capability of exporting these and monochromatic wave components. Again, this is Brandon's approach. And one thing I want to highlight here is that we are using this new NOAPSI feature where it allows us to export or import multidimensional fields that can have ungridded dimensions. And in the case of this N monochromatic waves, the ungridded dimension that we have is 6 or N number of wave components. But this also allows us to even import and export the full spectra. We don't have to define, say, 25 fields for each spectral element. We can just have one field of export or import, and it makes it quite convenient and computationally efficient. As for the MOM6 changes, I've been working on implementing this legacy WaveWatch 3 coupling that we have in CESM. This is Xing Li's work for POP2 and WaveWatch 3 coupling, where we pass an enhancement factor to CV mix based on the surface layer average and projected Langmuir number. And currently I'm in the process of testing and validating that. And the reason we are implementing this is to sort of have a test bed for future near-term development activities that we will be discussing next. And I guess with that, I can leave the floor.
Okay. Great. Thanks, Alper. Okay, so we've gotten through our discussion. We're only a couple minutes behind our intended schedule, and we have plenty of time left. So I know there's been a lot of discussion going through the chat. But like I said, I'm hoping that the panelists will kind of take over from here. I did, if people have this Google Doc open, put in a couple of questions to maybe guide the discussion. Bill, I think, nicely laid out a potential development pathway with some indication of priorities. I'd like to see some discussion or consent or rejection of that approach. And then maybe talk about, where are the rate limiting steps? What are the pieces of that we have to wait for versus what things can proceed in parallel? In terms of our ocean working group, we've basically dedicated half of Alper's time that is dedicated to the ocean working group, which means a quarter of his time to this wave project for the next, say, 6 months. So that's a resource we have in hand. What else is available and what do we need? What observations or additional LES calculations might we need to help guide this implementation? And are there, between the sea ice and the coupling to boundary layer physics, et cetera, maybe some of the human dimension applications, are there any conflicting requirements that we might need to think about and try to resolve? So anyway, I will turn it back to the panelists, and I guess I'll start calling on people. Gokhan, you had your hand up.
Steve was before me, actually. I'll let
Okay.
Steve, yeah, go ahead.
Go ahead, Steve.
I have a question for Baylor the Sailor. And it may be too technical for this, and if so, the moderators can say, skip it. But you said something about the coupling between the Stokes and the sort of Eulerian flow, and you said, it sounded like you were saying there is no coupling, but there was if you expand the product out in the kinetic energy term, for example, you get a US.UH term. I was a little confused about that. I don't know if you remember enough to know.
No, there's a linear coupling. And so a linear coupling doesn't jump across scales. You need a nonlinear coupling to have a scale to scale, like to make your parameterization, say your parameterized wave effects interact with your resolved wave effects. You need to jump scales to do that. And this equation set doesn't have that capability.
What
the
do you
real
mean by,
waves in the real world do, but
what
the
do you
wave
mean by
equations don't.
What do you mean by linear coupling? I mean, coupling is a U times a U term, right? And that's a nonlinear term.
No, so it's a U times a U Stokes term, and that's different because they're generated from different parts of it. So say that they would have a different wave number in general, and so you don't get that sine K1x plus sine K2x flipping out of from scale to scale the way you do in turbulence. So it's a simpler problem because of the overriding simplifications in the wave averaged equation set in the beginning. So I can show it to you more slowly, but I think that's the
okay.
simple point.
Thanks.
Okay, Gokhan, go ahead.
Yeah, it's since the equations went by quite fast, so this might be for Baylor the Sailor or Brandon question. So in the momentum equation, every single term is modified excluding the diffusion term. So the diffusion of momentum is still acting on the Eulerian, and presumably there's a reason for that. So that's one question. The tracer equations are not modified; they are still being they're still using the Eulerian, and probably there's a reason for that. And then the third question that I was going to ask is, given that the momentum is now most of it is using the Eulerian plus Stokes, when we compute the wind stress terms or other surface flux components in the coupler, what relative wind are we supposed to use?
Brandon, do you want to answer that?
All right, so I guess with
I'll
the
just say
first
a lot
part,
of these are still research questions, but
yeah, so with the first question asking if the friction term needs to be on the Eulerian current or the Lagrangian current, I think that's still a research question, and some of that hints at what Bill was talking about related to the directionality. There are some indications that mixing is actually down the Lagrangian gradient, though you're mixing the Eulerian momentum. Very much a research question, I think.
Tracer acting, yeah. Second is the tracer still is seeing the Eulerian.
So the tracer advection is the Lagrangian.
Oh, still like, okay, that's Lagrangian. Okay.
Yeah.
And then the last one was the relative wind issue.
So it doesn't actually, it probably doesn't make too much of a difference which one you used, but the surface flux is importantly different. Depending on how you treat the very near surface. In LES, traditionally, they have used the Eulerian field for the surface flux condition. And so you would probably have the Eulerian field for the wind, for the relative wind calculation. But it's not obvious to me that that's the right thing to do.
So they're all research questions like this. Okay, thank you.
But not the Lagrangian one. The Lagrangian one is clear. It's definitely the Lagrangian advecting everything.
Okay, Peter Sullivan.
Yeah, I was curious about when Baylor was talking about statistical waves. I guess the question is, most of the time, the ocean's got non-equilibrium winds and waves, especially when you have swell, things like that. That's one part of the recipe. How does it account for that? The other thing is we talked quite a bit about Wave Watch 3, and I guess we've kind of assumed that it's just perfect, but it's got some pretty empirical terms on the right-hand side, especially how waves grow and how they dissipate. The dissipation could be really important in nearshore regions, things like that. And is there any thought, are you just counting on the Wave Watch 3 developers to fix those up?
Yeah, so let me comment quickly, but I think Ching or Brandon might also have thoughts about this. On the first part, yes, the statistical waves is not a fully developed wave theory. It is trained against the level of non-equilibriumness that is present in WaveWatch, which seems to work pretty well. But it is also not capable of doing a lot of the things that we traditionally would think of as being important for non-equilibrium waves, like crossing swell. Crossing swell is missing, but it is not missing in the sense that it's the degree to which it reduces the magnitude of the Stokes drift on average is present, even though we don't actually know what direction the Stokes drift is going other than to assume it's in the wind direction. So for the specific, very rose-colored lens of looking only for Langmuir mixing, it seems to be pretty decent at doing its job. But the questions that we were talking about in the chat, we think it's going to do a quite poor job if you tried to predict other wave statistics. And that's what we need to think about more. But it might be good enough for climate use. That's really the point. And then why did we use WaveWatch was essentially because we didn't want to become wave model developers, and NOAA was happily doing that on their own. So we thought it was better to partner with them and leave that to them, and then just highlight the pieces of the story that we're missing, rather than trying to do the fundamentals that the wave community has been working on since Hasselman in the 60s.
Oh, no, that's fine. It's I guess the non-equilibrium problem seems kind of, well, from a research point of view, it's pretty interesting, because let's say the winds fall and the waves stick around, they're going to mix. And I mean, it's an LA regime that's really small, and that happens.
It surely does happen in the real world. What the question is whether it happens often enough that from a climate application perspective, it's worth the additional cost of WaveWatch over something like statistical waves. And I think that's the system that's being built here is really up to the user to decide how accurate they want their wave field to be. And so we have both paths available.
Yeah, I just mentioned that Baylor knows already, but Stephen Belcher and his graduate student, they looked at the climatology of waves, of essentially wave age, and it's pretty non-equilibrium over most of the planet.
And yeah, as I said, we didn't assume that we would have the same result as essentially what they have effectively if we had calculated a wave age statistic. It's not a fully developed wave theory.
The other thing is, will it do hurricanes, that kind of thing? I mean, you make hurricanes in CSM, I guess, but and with super complicated wave fields.
I think that's Brandon's territory for sure.
So do you mean specific to the theory waves or with WaveWatch?
Just in general, it seemed like you answered you put your good thoughts on that question, whether you should be running WaveWatch under a hurricane or the applicability of it, et cetera.
Yeah, I mean, I think a hurricane scenario is one where I would expect the theory wave stuff to start to do a bit less of a good job, you know, because we have such a different wave field on the right-hand side of the storm versus on the left-hand side of the storm because of this kind of coupling with the waves that are going in phase with the storm. WaveWatch itself, especially the latest versions of WaveWatch 3, so to kind of go back to your first question, WaveWatch has a number of source term packages, so a number of these parameterizations, maybe you know this. And so these would be open, I think, to the group if you're taking the latest version. And these more recent versions of WaveWatch definitely have better dissipation functions that are meant to actually, and the wind input term especially, to capture the hurricane fields, and they do a pretty good job.
Yeah, no, that's fine. I was just, because you're going to encounter everything. You're going to run the model, and it's going to hit all kinds of different regimes.
Yeah, absolutely.
Since I mean, the motivation for this discussion on theory wave, data wave is largely driven by cost questions. I thought, Alper, could you share that last slide you had on timings, which seemed not as scary as the numbers Baylor was putting up?
Well, I guess Baylor is comparing it against PUP, but I was comparing against MOM, which is
it's a more expensive ocean. Yeah.
Let me
and I guess while Alper's doing that, CC had some questions about grids, and also a question to Alper about if you're working on WaveWatch 3 history files. Now, maybe you could address that, what you're doing with history files from WaveWatch 3 right now.
So for these performance results, I just turned it off. But yeah, for validation, I was turning on all of the available history fields. But yeah, for the performance, again, these results are very preliminary. I did not optimize the time steps or the processor layout. But if you look at the case where we run WaveWatch 3 with the coarse grid, the cost is pretty minimal, like 2% of MUM6. But if we run them on the same grid, WaveWatch 3 cost is almost the same as MUM6, but the throughput is slower than MUM6. I guess this is also because WaveWatch 3 does not scale as well, or I did not manage to make it scale. But yeah, I guess it needs to be studied. But yeah, these are some preliminary comparisons.
And CC, did you have a different question about history files? What wasn't clear to me exactly what you're addressing.
So these numbers are, well, I didn't run it with MOM, but it's kind of more my impression that it's comparable to the ocean. But well, I guess you mentioned, Alper, that you actually turned off the history file, which I think is probably a big factor, because as far as I can tell, there's no parallel IO option. It's always just doing IO on one processor. So restarts are slow, history files really slow. And all of, it's reading in a lot. I think currently it reads in the wind every time step too. So just all of the IO could be improved, I think. Is that your impression too?
Yeah, I guess that applies to MUM6 to some extent as well, but yeah, I agree.
Not a fun job, but.
Yeah, okay, Bill? Large?
Yeah, I wanted to just float a couple of things. I mean, is it a plan, or could it be part of the plan to have a static version 6.07, the one that's just been implemented? Cece, it looks like your ice stuff's been put in there. So that would be a good thing to at least discuss whether that's static. And also, we seem to be running on the ocean grid, whatever it is. Would we want a static wave watch grid that we ran wave watch on and then interpolated? I don't know the answer to that, but I think if we get some guidance here, at least for this first implementation and beyond, it would be helpful to know if we can simplify things like that.
Some response to that? I think some of
DC,
the
is
discussion.
607 okay for you? Could you move to that?
Sure, I have no idea. But just as far as the resolution, I think we need in the CIs, we haven't really tested it because I haven't spent any time changing grids, which is part of our future plans. But my guess is that the pop grid, is kind of optimal for the CIs in some regards because of converging meridians, and so it's only increasing the latitude separation, which is already fairly decent at the 1 degree model grid. So we're happy, I think, with that, but we may be happier when we find out we may change that perspective if we go to finer resolution.
Chris and I have talked a lot about extending the machine learning approach that's presently speeding up the code to maybe also be a parameterization of downscaling from coarse waves to finer waves, but that's very much research.
Yeah.
Okay, I just want to try to, I'm scanning the questions. If people have posted in the chat, they want to bring something to the attention of the whole group, please feel free to speak up right now. Okay.
So I'll ask a question back to Brandon. I mean, it looks like we should plan to bring in not only the 6 surface Stokes drift components, but have a potential for a variable exponential decay. It could be all the same for now, but we should, like you had in your equations, I think you had a decay sub I. So we could just assume that that could be different. It's one more variable, it's nothing.
So I guess the point, Bill, that I was trying to make there is that we could have 6 different decay scales, but they can be fixed in space and time.
Right, exactly.
I think that's probably sufficient, although you could, of course, consider, passing whatever the peak wave number is of that specific partition as well, if you think those details are worth it. I'm not sure. Once we get up to n equals 6 or so, if that will make much of a difference.
Well, my thinking is, and we can discuss this, is that this first implementation we want as, fairly soon, so we can try some of these things out. We're not sure whether this has an order 1 impact on circulation or does almost nothing. And I think finding that out will dictate an awful lot of how much more effort we put into various things. And we also want to make sure that it's easy to experiment in various parameterizations and stuff and what you want to look at. So any more discussion about whether the output from a 1 cycle ocean ice run would be sufficient for a lot of people, that would be good too. That's the plan at the moment. But we don't know whether this is really a critical thing or subtleties. So, and the other thing I haven't heard, and is Nikki still on the line, is anybody taking on the idea of wave dependent air sea fluxes?
I don't know of anyone taking that on. I don't know if you can hear me right now.
Yes, we can.
Okay. But I see what I was thinking is I see potential in lots of different directions here for biogeochemistry, and even also outside of the biogeochemical realm for satellite simulation of surface roughness, emulators, right, in CESM, that we have to do other things. We know surface roughness and bubble injection both play really important roles in gas exchange, and the parameterization development for those continues indefinitely, right, for all of time. But the idea of having a framework in which to test those, I think using a model would be really cool. So I'm just excited about where this could go, but I'm certainly not volunteering to do anything.
Well,
at this
if
moment.
you could, why don't you try and see if there's anybody in that community would say, at least here's the wave parameters I might want. And then we can at least try and put in some, dummy kinds of transmissions and things. That would be useful.
Yeah, I could reach out to Rick Wanenkoff, who is really keen to think more about parameterizing waves in gas exchange processes and see what he has to say.
I think Jim Edson has worked on that problem to some extent as well.
Yeah, he keeps saying that the variance, that the waves are too poorly known to actually reduce variance in the fluxes, but that's an observational perspective as opposed to a modeling perspective.
I think it's a very wise, practical perspective myself. But except for gas exchange, that's quite a different kettle of fish.
I also think that the high wind regime of the Southern Ocean is of particular interest. The idea of like capturing these really intense storms and their effect on gas exchange and so on. So something to focus more than just sort of this global picture, more regional studies could be cool.
And Cece, I have one more question for you, if you're there. I said something about one wave coupling. It sounds to me like the WaveWatch model has to receive the ice edge or something.
I hope it would. Yes.
Does it now in your versions?
Oh, yes.
So it's not one way. I should correct that. It's not one way.
It was in CESM 2, but not in our.
It's one way from the ocean model. The ice, it gets the winds and it gets the ice extent. Okay.
It gets the ice fraction now too.
Okay, that's good.
But it's a very simple coupling from the ice to the ocean, or sorry, ice to the surface waves.
Sure.
Okay, Bob Hallberg.
So there was a comment a couple of minutes ago about holding off on putting in the effects of the waves on gas exchanges and things until we understand it better and can capture the observations. From a climate modeler's perspective, I think there's an awful lot of value in exploring whether there are amplifiers or sensitivities that could arise from that coupling, even if you can't demonstrate that it is accurate based on observations. As long as we do something plausible, you could write a lot of papers to help explore kind of the fat tails of our distributions. And so I would not wait until we have kind of solid observational calibration of our parameterizations to start exploring these ideas. I think they are very much worth exploring kind of in a more speculative way.
Yeah, if I can, I want to follow up on Bob's comments. So there are existing parameterizations for C-state dependent LRC fluxes, although maybe not very accurate, but they depends on common wave statistics like significant wave height or wave stiffness. So I guess that can be a first step for incorporating more wave effects in CSM. And another comment is on the theory wave. So in evaluating the theory wave, we really need to consider what are we going to use the wave information, right? So some wave parameterizations are sensitive to how well you get the wave statistics, but some parameterizations are not. So because our goal is not to like approximate the wave climate, right? So that's the goal of WaveWatch. But so our goal is to do a good wave parameterizations in CSM. So we really need to consider the different wave parameterizations we want to include in CSM.
Okay, thanks, Ching.
So Ching, can I ask you, I think we do need somebody to at least talk to and guide us in in any of these, even the preliminary ones, like Bob was mentioning, just so we're not way out of, do you have any suggestions on who? On the gas thing, I heard Rick Wanikoff might be at least approachable, and perhaps what about on anything else? Just somebody to talk to and get some, because some of it gets very elaborate very quickly, and we need to have a sensible approach, I think, for this first implementation.
So I know a grad student in Georgia Tech who is very interested in the wave parameterizations in CSM, and he's starting to run some CSM simulations with like the laminar turbulence parameterization. And he is interested in looking at the RC C-state dependent RC fluxes. So I'm not sure whether he will actually implement the parameterization in CSM, but yeah, I don't know. I don't know who is going to do the job.
I just mentioned that Jim McWilliams, former student that's at LSU, Zhang Lin, is really interested in how bubbles, etc., modify fluxes. He's written quite a few papers on that topic, especially with regard to hurricanes and high wind conditions and things like that. He knows an awful lot about the topic.
Thanks, Peter.
Bill, I was going to ask you, if I could just switch gears just a tiny bit, whether you were thinking of all the changes to the boundary layer parameterization that you worked on the last few years, whether that's part of the intent of modifying MOM6 or not, or what is your...
No, the intent right now is to get the infrastructure to do such, for anybody to do such things.
I see.
Okay?
Yeah.
And to try and find observational evidence or LES evidence for what capabilities we need. But what the answer is going to be, I have no idea, and where we're going to end up. And as I say, whether this is order 1 or order epsilon kind of effects.
Oh yeah, so no, but I think
discussion right now.
Yeah.
And I
Yeah. Brandon mentions that he's worked a lot with Luke at Princeton, stuff like that. I was curious because when waves break, they essentially create a surfing effect, which really increases Stokes drift quite a bit. And maybe that's too much of a researchy kind of idea, but there's potential that when there's breaking, you end up with a lot more wave effect, especially as it goes into the Stokes drift than if it's not. And maybe that's just a research question.
Yeah, and it's certainly a WaveWatch wave modeler question. I suspect they would have to try and come up with such a enhancement, I would think. But right now, we have 0 Stokes drift, so it's not too hard to do better than that.
Oh yeah. No.
Or we used to have. We're getting there now. And so
no, it's great. It's great.
Let's take sensible steps. Is what I'm thinking.
No, I greatly I give kudos to all the worker bees who are actually trying to take fancy ideas and turn them into a real model. It's really good.
Yeah, there's a lot of beautiful stuff, especially out of like Ken Melville's Wave Lab, which is many generations ahead of where we will be for a long time.
Oh no, it's gorgeous. It's if you look at the breaking statistic as a function of wave age, it's just fabulous.
Well past noon, but that's okay. I think we have the Zoom call for another 20 minutes. I do want to sort of put out there the question to the group that Bill kind of laid out a plan that we have for how we are going to focus our internal resources. I'd like to give anyone outside of our group the opportunity to comment on that plan and maybe gaps or dependencies or other considerations that we should be taking into account in the next several months. Gokhan had a question.
Yeah, mine is not related to that one, though. Bob is, I think, related to that one.
Bob?
So this is not related to waves, but it is related to the heat budget. I think Bill put out very early in the conversation today the idea that if the atmospheric people are giving up once they get below about 1/10 of a watt per meter squared, we shouldn't try to do any better. And I've been mulling this one over for a few hours, and it just doesn't
Peter
feel right.
Lauritsen's number was more like 1/1000th of a watt per meter squared.
Oh, 1,000.
Yeah, it was 0.01. I know anything lower than that, he was, yeah, it was 0.1.
At least 0.1, yeah. Yeah, it wasn't tenths. It was smaller than that.
100.
But regardless, I would be a little bit reticent just to take atmospheric numbers where radiative damping to space limits how long things can accumulate, and necessarily apply the same thinking to the ocean where heat in the deep ocean can be sequestered for and accumulate for 1,000 years. I think we probably are going to want to be a little bit do a better job of conserving enthalpy in the ocean than our atmospheric counterparts are willing to do.
So Bob, when Frank was mentioning this global fixer to do that, your global fixing at about the 0.01 watt per square meter that was for your fear that it might accumulate locally somewhere. But I think we have to be careful, yeah. And one of the big reasons to do this is to make sure you've got a budget that sort of closes so that if somebody puts something in and screws it up, you know. And right now, the atmospheres aren't conserving things.
So on the ocean side, we conserve enthalpy, heat, separately from kinetic energy. And we don't convert dissipated kinetic energy into enthalpy.
Right.
The enthalpy budget is something we close to like 18 or 19 decimal places, although there are things like the radioactive decay of potassium in seawater and heat from the metabolism of fish and other things that all start to come in at that sort of 100th to 1,000th of a watt per meter squared sort of level that we could take into account. But we have a very good closed budget for the ocean that has things in and has things out, and we rely on that. But we don't do this mechanical to thermal conversion, and probably could do it without too much pain. It's not a huge term in the ocean. It is a big term in the atmosphere.
Yeah, it just takes someone to do it. It's doable.
Okay. Any other some hands? I can't tell whose hand's still up and whose hand's newly
I
up,
still have a question quickly. Again, this is for Baylor and maybe Peter Sullivan. Baylor, when you gave your presentation, you indicated that some aspects of the waves cannot even be done with the LES. What aspect was that, and is it also not done in Peter's LES version model?
So Peter's LES is also based on the wave averaged equations. And there are some things that happen near the sea surface that are phase dependent. So some observations show that there's mixing that occurs in like only the crests of waves. And in addition, there's white capping, which is explicitly disallowed because it's a steep slope event. So those pieces stay out of the wave average equations. The wave average equations seem to be quite good at describing things like Langmuir turbulence. So there are very near surface effects that are missing, and Peter should comment on what he thinks the solution to that problem is, but that's a well-known part of it. What I was talking about is just in the analysis framework, especially the wave average equations really only depend on Stokes drift, and the Stokes drift statistics are very large scale and very slowly varying. That's not actually true of waves themselves. There are small scale couplings, particularly in the surf zone, but also in the open ocean, of wave current interactions that occur on the wavelength of the waves themselves and are therefore not describable with Stokes drift at all. So we're doing a decent job of bringing in a simplified equation set in appropriately, but we know that they're missing pieces.
Thank you.
Gokhan, would you like me to say something or not?
No, that's okay. In the interest of time.
No. One of the cool tests that people have done in the past, I'll make it real quick, is to take actually a wave resolving LES with a wavy surface at the top, okay, and compute it as best you can, and then compare it to CL asymptotics. It's so far, it shows that it's pretty good, but there haven't been enough of those kinds of calculations. To do phase resolve waves is pretty daunting, but it's doable. It's just too busy with so many things.
Thank you.
Anyone have a final thought or comment on the wave discussion? Bill, are you happy with where we're at and have an idea of how we should be investing our resources in the next couple of months?
Yeah, well, I think I have some names of people to contact to see if we can do some more simple things, especially on what we might want on the RC flux issue. Especially if Nikki can take on contacting Rick, or just, yeah, I think I know who to contact now. And then probably we should broadcast a more of a detailed plan. Yeah. But I haven't heard anything. I've asked the questions I needed to, and I think I got answers, except for the grid. It seems like we could actually concoct a static grid that satisfies everybody's need that might not have anything to do with the ocean grid at the time, is worth thinking about. And then that's static, and then we just keep working on that and worry about interpolating these things. Might be I guess a static thing that's not varying underneath us when we do these experiments. But I haven't heard enough debate on exactly what grid to use yet. That's what I'd like to know. Especially near the coast and things like that. Should you telescope near the coast? That kind of stuff.
Any input on that question? Let me make it a little more concrete. I mean, I guess my thinking was that our default starting point would be to be running MOM6 and the waves on the same grid. Does anyone think that is a bad idea?
It might be not so great at 1/10 of a degree resolution.
Well, we're talking about a 2/3 grid for right now.
I think so.
In terms of getting our infrastructure in place and getting the Stokes profiles into the ocean model and that kind of thing.
I think regardless of what happens, we're going to want that one. We may decide to coarsen after or refine after, but that one will be an important central case.
So you're talking to run on the same grid? So I just want to make sure to point out, we still don't have full capabilities for a tripolar grid in WaveWatch, though that is something that's in progress. As long as there's ice there, you're fine. But if there's not ice, you have basically the model's going to blow up.
I thought that Alper was running on our tripole 2/3 grid.
Yeah, so it didn't blow up for a couple of months, but maybe I did something wrong.
Did you have ice or was it open ice?
There's ice.
Yeah, that's going to save you. I can talk to you guys more about this.
Okay.
Oh, yes. Well, I would say one thing. I think whatever for these kind of questions, I think whatever we do, we should both do the same thing and pool resources here so we can get on to the implementation. And so I wouldn't want to go two different routes yet.
All right.
Brandon, EMC is actively working on fixing this. Jessica is working on it very actively, so we're not we're not looking at having to identify new resources to make WaveWatch work on a tribollar grid. It's something that will be happening for basically for weather forecasting problems and things like that that are kind of outside of the resource scope of this conversation, right?
Possibly. It's maybe a bit more complicated conversation than that, but it is on EMC's radar, definitely.
Okay. Any broader questions, ocean working group issues we can address for you in the last couple minutes here? Okay, I have a question to Ryan or Todd. How do I save the chat to a file?
I'll go ahead and do that.
Okay, thanks, Todd. I'll want to refer back to those notes. Okay, well, thanks everyone. I hope this, I think it was successful. I hope everyone shares that view. I think as several people have said, this is an exciting new direction for the Ocean Working Group, and it seems to be a lot of interest and enthusiasm across the community. So something we're going to push on in response to that enthusiasm. And be in touch and hope to see everyone at the Winter Working Group meeting. So long.
Take care, everybody.